The ship of Theseus is an old thought experiment that asks a simple question. If you replace every part of a ship over time, is it still the same ship? The story goes like this. There is a wooden ship in a museum. Over the years, its planks start to rot. One by one, workers replace the old planks with new ones. Eventually, every single part of the ship is new. None of the original wood remains. So, is this still the ship of Theseus? This question leads to a deeper issue. What makes something the same over time? Is it the material it's made of, or is it something else, like its shape or history? People have debated this for centuries. Some say the ship is still the same because it has kept its form and function. Others say it is not the same because the material is different. Now imagine someone collects all the old planks from the original ship and builds a new one using only those parts. Is this second ship now the real ship of Theseus? It has all the original material, but it wasn't built in the same place, nor does it follow the same timeline. It does not have the same continuity as the ship that stayed in the museum. So which one is the real ship of Theseus? The one with new parts in the old spot, or the one with old parts rebuilt somewhere else? One way to approach this is through metaphysics, which is the study of what things are and how they persist over time. Some philosophers say that identity depends on continuity. In that case, the ship that stayed in the museum, even with new parts, is the same ship. It followed a steady line of existence. It never stopped being the ship of Theseus, even as parts were replaced. This is similar to how people stay the same person, even though their cells change over time. Others focus on the material. They argue that once the original parts are gone, so is the original object. To them, the new version in the museum is just a copy, not the same ship. In this view, the second ship, the one built from the old parts, might have a better claim to being the original, even though it lacks the continuity of location and use. There's also a more modern way of looking at it. Today, many thinkers believe the answer depends on context. In some cases, what matters most is function. If the ship still sails, holds people, and looks like the ship of Theseus, then it still is. We can call this functional identity. In other cases, the material matters more. In a historical setting, the value of an object might come from its original material. Museums often care about what is original and what is not. Take an example from daily life. Think about your phone. Over time, you might replace the battery, the screen, or even the frame. As long as it still works, you think of it as the same phone. But if you replace every single part, including the processor, is it still your phone, or is it a different one that just feels familiar? Now consider a more personal example, your body. Almost all the cells in your body are replaced over time. You're made of different material than when you were a child, yet you feel like the same person. You have the same memories, the same name, and a continuous life. If someone said you were not the same person, that would feel strange. So here, continuity matters more than material. In contrast, think about a signed baseball. Its value comes from the signature. If someone replaces the ball but copies the signature, it's not the same thing. The original material is what gives it meaning. So in this case, the material matters more. We can also look at legal examples. Suppose a building is declared a national monument. Over time, it is restored and old bricks are replaced. The law still treats it as the same building. But if someone builds an identical replica elsewhere, it is not the same under the law, even if the materials are more original. These examples show that identity is not always simple. In some situations, we care about history and continuity. In others, we care about material or function. That's why modern thinkers often say that the answer to the ship of Theseus depends on how we define identity for that situation. A computer can help us see this in another way. Say you have a computer that you upgrade piece by piece. First, you add more memory. Then you change the graphics card. Later, you swap the motherboard. Eventually, you have changed every part. Is it still your computer? You might say yes because you upgraded it step by step, always thinking of it as the same machine. But if someone else takes the old parts and rebuilds a working version of your original machine, which one is yours? These questions don't always have one clear answer. It's not just about logic. It's about how we think and what we value. For example, companies sometimes use the idea of continuity in branding. They may change their entire staff, building, and even their product, but keep the same name. Customers still see it as the same company. That's because the identity of a business is tied to its name, purpose, and reputation, not its material parts. In the end, the ship of Theseus helps us think about identity in a deeper way. It reminds us that sameness is not just about material. It's also about history, use, and purpose. Whether we are talking about ships, phones, or ourselves, the answer often depends on what we choose to focus on. The question may not have one right answer, but that's what makes it valuable. It teaches us to ask what really matters when we call something the same. Zeno's paradox about Achilles and the tortoise is one of the most famous problems in philosophy. It goes like this. Achilles, a fast runner, is racing a tortoise. To be fair, he gives the tortoise a small head start. Once the race begins, Achilles quickly reaches the point where the tortoise started. But by that time, the tortoise has moved a little farther. Achilles then runs to this new point, but again, the tortoise has moved ahead. This process continues. Every time Achilles reaches the tortoise's last position, the tortoise is slightly farther ahead. So, Zeno says, Achilles will never catch up. At first, this seems silly. Of course, Achilles will pass the tortoise. He is faster. In real life, we see this kind of thing happen all the time. But Zeno's argument challenges our understanding of motion, time, and space. It makes us think harder about how movement works and how we measure it. Paradox is built on the idea of infinite division. Zeno breaks the race into an endless number of steps. First, Achilles must reach the point where the tortoise began. Then he must reach the point the tortoise moved to after that. Then the next point, and so on. Each of these steps is shorter than the one before, but there are infinitely many of them. So Zeno asks, how can Achilles finish an infinite number of tasks? If he can't, how can he ever pass the tortoise? This sounds like a serious problem, but mathematics gives us a clear answer. The key lies in understanding infinite series. When you add up an infinite number of things, the total does not always grow without limit. Sometimes, even an infinite series can have a finite sum. Take a simple example. Start with the number 1, then add 1/2, then 1/4, then 1/8. Each new number is half of the one before. This pattern continues forever. Even though you are adding an infinite number of terms, the total approaches a limit. In this case, the sum gets closer and closer to 2. It never goes over 2, and it gets as close to 2 as you want. This is called convergence. The infinite series adds up to a finite value. Now think about the race again. Suppose the tortoise starts 10 meters ahead of Achilles. Achilles runs 10 times faster than the tortoise. So when Achilles runs 10 meters, the tortoise has moved 1 meter. When Achilles runs that extra 1 meter, the tortoise has moved 1.1 meters. Next, Achilles runs 0.1 meters, and the tortoise moves 0.01 meters. This continues. Each time, the distance Achilles must run gets smaller. The total distance he must cover is 10 plus 1 plus 0.1 plus 0.10 plus. This is a geometric series. Each term is 1/10 of the previous. The sum of this series is 11.111, etc. Repeating. Mathematically, this adds up to 11 1/9 meters. Achilles can run that distance in a finite time, so he does pass the tortoise. Zeno's mistake was in thinking that an infinite number of steps means infinite time. That's not true. If the steps shrink fast enough, the total time or distance stays finite. In the race, Achilles does take an infinite number of small steps, but they add up to a limited distance because he runs faster. He finishes those steps before the tortoise can stay ahead. You can compare this to folding a piece of paper. Suppose you fold it in half, then again in half, and keep folding. Each fold makes the paper smaller, but you can't keep folding forever. Eventually, the folds are too small to matter. Similarly, the steps Achilles takes become so short that they stop making a real difference. Another way to understand this is with time. Suppose it takes Achilles 1 second to reach the tortoise's starting point, then 0.1 seconds to reach the tortoise's next spot, then 0.01 seconds for the next. The total time is 1 plus 0.1 plus 0.01 plus etc. This adds up to about 1.111 seconds. That's not infinite. So in just over 1 second, Achilles passes the tortoise. Zeno's paradox is not really about running. It's about how we think of space and time. In ancient Greece, they didn't have the tools we have now. They didn't have calculus. They didn't know how to deal with infinite sums. So when Zeno made this argument, it was hard to answer. Today, we can explain it with basic math. Still, the paradox makes a good point. It shows that common ideas about motion can be confusing when you look closely. It pushes us to ask, what is motion really? Is space continuous, or does it have smallest units? Can time be broken down forever, or does it stop at some point? These are still good questions. In physics, people study the limits of time and space. Some theories suggest there is a smallest possible distance, called the Planck length. If space has a limit to how small it can be divided, then the idea of infinite steps may not apply. But that is a question for quantum physics, not for everyday races. In regular life, the paradox does not hold up. Achilles passes the tortoise. Math shows us how. The sum of infinitely many small steps can be finite. That's the main idea. Once we see that, the puzzle disappears. But the lesson stays. It reminds us that even simple things, like a race, can hide deep questions. And sometimes, to answer them, we have to think in new ways. The barber paradox is a simple story that leads to a deep logical problem. Imagine a village with one barber. He has a rule. He shaves all the men in the village who do not shave themselves. He does not shave anyone who already shaves himself. Then the question is asked, does the barber shave himself? If he does shave himself, then he must not shave himself, because he only shaves men who don't shave themselves. But if he doesn't shave himself, then he must shave himself because he shaves all men who don't shave themselves. Either way, we run into a contradiction. Both answers lead to a problem. This is not just a trick or wordplay. It points to a serious issue in logic. It shows what happens when we try to define something in terms of itself. That is called self-reference. The barber's rule includes himself in the group he is shaving, and that causes the problem. You can think of it like this. The village is a set of men. Some shave themselves, some don't. The barber shaves only those who do not shave themselves. So he creates a group, call it Group A, of people who do not shave themselves. He shaves all of Group A. Then someone asks, is the barber in Group A? If he is, he does not shave himself, so the rule says he must shave himself. But if he is not in Group A, that means he does shave himself, so by the rule, he must not. The definition collapses when applied to itself. The problem is not the barber or shaving. The problem is the logic used to build the rule. This paradox was made famous by Bertrand Russell, a British philosopher and mathematician. He used it to show a flaw in how people were thinking about sets in math. In his time, some thought any group could be treated as a set, and that sets could even include themselves. But Russell showed that if you let sets contain themselves in this way, you can create contradictions. To understand this better, think of a library. Suppose the librarian decides to create a catalog of all books that do not list themselves. If a book includes itself in its own list, it is not in the catalog. If it does not include itself, than it is in the catalog. Now the question becomes, should the catalog list itself? If it does, then by rule, it should not be in the catalog. But if it does not list itself, then by rule, it should be in the catalog. Again, you get a loop that makes no sense. That is the same problem as the barber. These kinds of problems are not just riddles. They show that our rules for building logical systems can break if we are not careful. In math, this led to changes in how people define sets. Instead of saying any collection of things can be a set, modern set theory includes rules to prevent sets from referring to themselves. This avoids the kind of contradictions seen in the Barber paradox. Another example of self-reference is the liar paradox. It goes like this. A man says, "I am lying." If he is telling the truth, then he must be lying, as he said. But if he is lying, then he is telling the truth. It's a loop with no clear answer. Like the Barber paradox, it shows what can go wrong when a statement includes itself in its own claim. In programming, self-reference can also cause trouble. A function that calls itself without a way to stop can cause a crash or endless loop. That's why programmers use clear rules to handle recursion. They set limits to avoid repeating forever. Logical systems need the same kind of limits to stay consistent. In the case of the barber, the way out of the paradox is to admit that no such barber can exist. You can't have a person who shades exactly those who don't shave themselves, including or excluding himself. The rules don't allow for it, so the situation is impossible. It can't happen in real life because the definition breaks logic. This shows a bigger lesson. Not every idea that sounds fine in plain language can work in logic. We need to be precise in how we define things. If we build a system with loose rules, we might create contradictions. That's what Russell pointed out. The idea that any group can be a set leads to paradox. To fix this, new rules were made. One rule says that sets cannot contain themselves. This helps avoid problems like the barber. Even though the Barber paradox seems simple, it changed the way people thought about logic and math. It helped lead to the development of modern set theory, which uses strict rules to avoid self-reference. These rules form the base for many areas of math, including how we design databases, build programming languages, and structure logical arguments. So the Barber paradox is not just a joke or a puzzle. It's a sign of how hard it can be to define things clearly. When we include a rule that refers back to itself, we risk running in circles. This is why logical systems avoid definitions that allow self-reference without control. The paradox helps us see where logic needs boundaries. When people ask whether the barber shaves himself, they are really asking whether a system can include itself in a clean, logical way. The answer is no, not unless we change the rules. That's why the Barber paradox is unsolvable within normal logic. It's not that we don't know the answer. It's that the question cannot be asked in a way that works. Once we see that, we understand how important structure and limits are in logic and math. The grandfather paradox is a classic problem that appears when we imagine traveling back in time. The setup is simple. Suppose you go back in time and kill your grandfather before he has children. That means your parent is never born. And if your parent isn't born, you aren't born either. But if you were never born, how did you go back in time to kill your grandfather? That's the paradox. It creates a logical loop that doesn't make sense. This idea is not just science fiction. It shows a deep problem with the idea of changing the past. In everyday life, time moves forward. One event causes the next. You are born because your parents met. You grow up, make choices, and move through time. But time travel flips that. It says the future could affect the past, and that brings trouble. Let's look at it more closely. Imagine someone builds a time machine. You step into it and set the date for the year 1950, when your grandfather is a young man. You find him and somehow stop him from meeting your grandmother. As a result, your parent is never born. That means you are never born. But if you are never born, who traveled back in time to do all this? That's the loop that makes the paradox. There are a few ways to explain or resolve this problem. One of them is called the multiverse theory. It says that each time you make a change in the past, a new timeline forms. So if you go back and change something, you don't affect your own timeline. You just create a new one where events play out differently. In this case, you go back and stop your grandfather from having children. But that doesn't erase you. It just creates a world where you were never born, while you still exist in your original timeline. You can think of it like a fork in the road. The past splits into two paths. One leads to your original life. The other leads to the new world you created. This solves the paradox because it removes the loop. You don't erase your own existence. You just move into a new branch of time. Another idea is the self-consistency principle. This says that time travel can happen, but you cannot change the past in a way that creates a contradiction. If you go back in time, something will stop you from killing your grandfather. Maybe your weapon jams. Maybe you change your mind. Maybe your grandfather escapes. No matter what, the universe finds a way to keep the timeline consistent. This idea comes from physics, and it's linked to the work of people like Igor Novikov. It says that any action you take in the past must already be part of history. If you exist today, then nothing you do in the past can stop you from existing. This turns time into a kind of loop that always fits together. There's no room for paradox because the timeline always adjusts to stay stable. There's also the idea of the block universe. This view treats time as a single, unchanging structure. Think of it like a film reel. The entire movie, past, present, and future, already exists. You just watch it one frame at a time. In this model, all events are fixed. You can't go back and change the past because it's already set. If you travel back in time, you were always meant to do so, and everything you do is already part of history. This means you never had the option to kill your grandfather in the first place. Maybe you tried but failed. Or maybe you were the reason he met your grandmother in the first place. That way, the loop still happens, but without contradiction. It's like all events are frozen in place. You can move around them, but you can't alter them. These theories come from physics and philosophy. None of them have been proven in the real world because we don't have a working time machine. But they help us think about how time might work if travel to the past were possible. Each one has strengths and weaknesses. The multiverse theory makes sense in some versions of quantum physics. It matches how particles behave in strange ways, creating many possible outcomes. But it's hard to test. If each change creates a new world, we may never see those other worlds. The self-consistency principle has strong logic behind it. It avoids paradox by saying you simply can't do things that would create one. But it also limits your choices. If the past cannot be changed, then time travel becomes a kind of loop with no real freedom. The block universe view is the most strict. It says the future is just as fixed as the past. Some people don't like that idea. It feels like fate. Everything is set in stone. But in physics, this idea fits well with Einstein's theory of relativity. In that theory, time and space are part of the same fabric. You can move through both, but you can't change the shape of the fabric. Let's look at a simpler example. Imagine you go back in time and try to stop a fire. You think you can save lives, but when you get there, every attempt you make fails. The fire still happens. Later, you learn that your actions actually caused the fire by accident. That fits the self-consistency idea. You didn't change the past, you helped create it. What looked like free will was just part of a bigger pattern. Or take the multiverse view. You go back and stop the fire. In the new world you created, the fire never happens. But when you return to your own time, nothing has changed. You just made a copy of history where the fire didn't occur. Your own world remains the same. That might feel pointless or helpful, depending on how you look at it. The grandfather paradox shows us how fragile our ideas about time can be. It makes us question cause and effect. It shows that time travel is not just about machines or science. it's also about logic. If we ever discover a way to travel through time, we'll need more than engines and fuel. You'll need a clear idea of how cause and effect work when time is no longer one way. Until then, we explore these ideas through thought experiments, stories, and physics. Each theory offers a way to think about what time really means and whether it can ever be turned back. A liar paradox begins with a short sentence. This statement is false. At first, it sounds like a riddle, but if you stop and think about what the sentence is doing, you run into a real problem. If the statement is true, then what it says must hold, but it says that it is false. So if it's true, then it's false. On the other hand, if it's false, then what it says isn't true, but it says it is false. So if it's false, then it must be true. In either case, you end up in a loop. The statement cannot be clearly labeled as true or false without creating a contradiction. This is not just a game with words. The liar paradox shows a serious issue in logic and language. It's an example of what happens when a sentence talks about itself in a way that leads to contradiction. This is called self-reference. The sentence refers to its own truth or falsehood. That creates the loop. It's like standing between two mirrors and trying to find the original reflection. Each image points back to the other. Think about a label on a box that says, "Everything on this box is false." If you believe the label, then it must be lying. But if it's lying, then what it says is false. That would mean everything on the box is true, but that includes the label, which says it's false. So you're right back where you started. This kind of loop is not just a language trick. It affects systems that depend on clear definitions of truth. Mathematics, logic, and computer science all need to be able to tell if a statement is true or not. If a statement can be both at once or neither, then it breaks the system. Alfred Tarski, a Polish logician, offered one solution to this problem. He said that we must create levels of language to avoid confusion. In his view, we need to separate the language we use to talk about things from the language we use to talk about truth. For example, the sentence, "Snow is white," belongs to what he called the object language. If you want to say that this sentence is true, you move up a level and use the meta-language. In the meta-language, you can say, "Snow is white" is true, but you can't let the object language talk about its own truth directly. That's how you avoid loops like the liar paradox. Tarski's solution is called a semantic hierarchy. It keeps sentences from making statements about themselves unless they are in a higher level language. You can think of it like rules in a courtroom. A judge can speak about the law, but the law cannot speak about the judge. Each level has its own place, and crossing those lines creates confusion. Another approach comes from modern logic. Some logicians suggest we move beyond the idea that every statement must be either true or false. In classical logic, this is called the law of the excluded middle. But what if some statements belong to a third category? That's where three-valued logic comes in. In this system, a statement can be true, false, or undefined. The liar sentence would fall into this third category. It is neither true nor false because it cannot hold a consistent meaning. This might seem strange, but we already deal with unclear truth in everyday life. If someone says, "I always lie," do you believe them? If they are lying, then the statement is false, which means they don't always lie. But if they're telling the truth, then the statement is true and they always lie. That's the same loop as the liar paradox. You might decide the best answer is to say, "That statement just doesn't work." You reject it, not because it's false, because it doesn't fit into the true or false model. This is similar to how computers handle errors. When a program hits a rule it cannot resolve, it returns an error or undefined rather than crashing. In programming languages, this kind of logic is important. For example, a condition in code might be true, false, or not known yet. A system that can handle that third case can avoid loops and crashes. You can also look at this in terms of rules in a game. Suppose a rule says, "This rule does not apply to itself." That's hard to follow. If it applies to itself, then it says it doesn't. But if it doesn't apply to itself, then maybe it does. You can't write that rule in a consistent way. To fix it, you need to change the way the rules are written. You might split the rulebook into sections and say that some rules can only apply to the lower sections, not to themselves. A liar paradox is not the only self-referential problem like this. In the early 20th century, these issues caused major trouble in mathematics. Bertrand Russell found a similar problem in set theory. He asked whether the set of all sets that do not contain themselves includes itself. If it does, it shouldn't. If it doesn't, then it should. That's the same kind of loop. These paradoxes pushed people to rethink the foundations of logic and math. They led to more formal systems where rules are defined in careful steps. These systems include safeguards to avoid self-reference unless it's clearly controlled. Some thinkers go even further. They say that truth itself is a flexible concept. In some types of logic, like paraconsistent logic, contradictions are allowed. A statement can be both true and false without destroying the whole system. This idea is still debated. It changes how we think about truth. Instead of being black and white, truth becomes something more complex, like a spectrum or a balance between different meanings. Still, most systems today prefer to keep things clear. They either avoid self-reference using hierarchy or handle it using more values than just true and false. These approaches help keep logic stable. They allow people to build consistent arguments, develop proofs, and create programs that don't collapse when faced with tricky statements. The liar paradox shows the limits of how we talk about truth. It forces us to step back and ask, what does it mean for something to be true? And sometimes the answer is that the sentence itself doesn't belong in the system. It's not wrong, it just doesn't work. Like a rule with no clear meaning, it falls outside the structure we need to think clearly. And that's the lesson. Not every sentence is fit to be judged true or false. Some break the rules so deeply that they have no place in the game at all. The omnipotence paradox begins with a simple question. Can an all-powerful being create a rock so heavy that it cannot lift it? At first, it sounds like a clever riddle. But as you think about it, you realize the problem runs deeper. If the being can make such a rock, then it cannot lift it. So it's not all-powerful. But if it cannot make the rock, then it also isn't all-powerful. In either case, the being seems to lose its status as truly omnipotent. That's the paradox. To explore this, we need to look at what people mean when they say a being is omnipotent. Most of the time, people take omnipotence to mean the ability to do anything. That includes creating anything, changing anything, or acting in any way. But when pushed to the limits, this idea starts to run into trouble. The rock paradox shows that doing anything might include things that don't actually make sense, even in theory. Take another example. Can an omnipotent being draw a square circle? At first, that might sound like a valid task. But when you think about it, you realize that it's not. A square, by definition, has 4 equal straight sides and 4 right angles. A circle, by definition, has no corners and a round shape. These two ideas cancel each other out. The phrase square circle doesn't point to a real object. It's just a contradiction. So asking whether an all-powerful being can create one is like asking whether it can make an object that both exists and doesn't exist at the same time. In philosophy, this has led to a clearer way to define omnipotence. Instead of saying that an all-powerful being can do absolutely anything, many philosophers now say it can do anything that is logically possible. That means anything that doesn't involve a contradiction in terms. For example, it can create stars, move planets, or change the laws of nature. But it cannot make 2 + 2 = 5 because that's not a real task. That's just a misuse of language. With that idea in mind, the rock paradox starts to lose its strength. The question asks the being to do something that cancels itself out. It says, in effect, can you make yourself not omnipotent? Or can you fail to be unlimited? These are not genuine tasks, they're contradictions. It's like asking if you can win a game you've decided to lose. If you lose, you've succeeded in your goal, so you've won in a sense, but then you didn't really lose. If you win the game by normal rules, then you failed your goal of losing, so you've lost in a different way. The point is, the task itself doesn't work. It breaks its own conditions. Another way to see this is through the rules of logic. In logic, a contradiction is something that cannot be true under any conditions. For example, the cat is on the mat and not on the mat at the same time is a contradiction. It breaks the law of non-contradiction, which says that something cannot both be and not be in the same way at the same time. If a task depends on breaking this rule, then it's not really a task at all. It's a misuse of logic. When people first hear this, they sometimes feel like it weakens the idea of omnipotence. They think if there's anything the being cannot do, then it's not truly all-powerful. But that's not the case. The idea is that power means being able to carry out all possible actions, not being able to do what can't even be described in a coherent way. The limit is not on the being's power. It's on the language we use to describe tasks. Imagine someone says, "Can chef cook a meal so perfect that it ruins their career?" Or can an artist paint a picture so beautiful that they never want to paint again? These are not clear goals. They create confusion about what success looks like. The same is true of the rock paradox. If the being creates the rock, it succeeds in making it, but fails in lifting it. If it can lift it, it succeeds in strength, but fails in the task of making it unliftable. The task breaks its own conditions. This brings us to a key idea. The problem is not in the being, but in the question. Some questions are built in ways that don't make sense when examined closely. They pretend to ask something real but are shaped in a way that creates a trap. The rock paradox is one of these. To see this clearly, we can look at how logic systems work. In formal logic, statements must be internally consistent. You can't claim both that X is true and X is false in the same situation. If you allow that, then everything becomes meaningless. The system falls apart. That's why most logical systems treat contradictions as errors, not tasks. In theology, many thinkers accept this view. They say that God, or any omnipotent being, is not limited by this clarification. Being unable to do the logically impossible is not a weakness. It's just a sign that power works within the structure of truth and meaning. An all-powerful being can still create worlds, change reality, and act without limit within the realm of what makes logical sense. That's still absolute power. To make this easier to grasp, consider a programming language. Suppose you write a line of code that says, if x equals 1 and x equals 2 at the same time, run this function. The code won't work, not because the computer is weak, but because the condition doesn't make sense. The machine can't act on nonsense. In the same way, asking an omnipotent being to make a rock too heavy for itself is like asking a computer to run broken code. It's not a task, it's an error in the request. Another helpful example comes from rules in sports. Imagine a rule that says the referee must always follow the rules except when they don't. That rule cannot be followed. It breaks itself. It doesn't matter how skilled the referee is. The rule is flawed. The same applies to the rock paradox. The problem is in the rule, not in the one trying to carry it out. This way of thinking helps keep the idea of omnipotence both meaningful and strong. It avoids confusion by drawing a line between tasks that make sense and ones that don't. The idea is not to lower the bar, but to make sure the bar itself is real. When we define power as the ability to act within a logical system, we give it shape. We make it something that can be understood and explored. The rock paradox is still useful, not because it proves a problem, but because it teaches a lesson. It reminds us to be careful with how we frame ideas. Words can be twisted into shapes that don't hold up when tested. By recognizing that, we can think more clearly. We can see that power, even absolute power, has to work with the rules that make actions possible in the first place. That doesn't weaken it, it makes it real. A twin paradox is one of the most well-known puzzles in Einstein's theory of relativity. The story is simple. Two twins live on Earth. One stays home. The other travels into space at a speed close to the speed of light. After some time, the traveling twin returns. To everyone's surprise, the traveling twin is younger than the one who stayed on Earth. This result feels strange. If both twins are moving relative to each other, and shouldn't each see the other's clock running slow? Why does only one end up younger? At the center of this paradox is the idea of time dilation. According to Einstein's theory of special relativity, time doesn't pass at the same rate for everyone. When someone moves very fast, close to the speed of light, time slows down for them compared to someone who stays still. This isn't just a theory, it has been tested. Scientists have used very accurate atomic clocks on airplanes and satellites. These clocks show that time really does pass more slowly for moving objects, even at regular speeds. To understand how this works, imagine the traveling twin gets into a spaceship and flies away from Earth at 90% the speed of light. The ship travels for 5 years, according to the ship's clock, then turns around and comes back at the same speed. The full trip takes 10 years for the traveler, but back on Earth, more than 10 years have passed, maybe 20 or 30, depending on the exact speed. When the twins meet again, the one who stayed on Earth has aged much more. The reason this feels like a paradox is because of symmetry. From the traveler's point of view, the Earth is the one moving. So why doesn't the twin on the ship see the Earth-bound twin aging more slowly? Shouldn't both see the other as aging slowly? That's what makes it seem confusing. The answer comes from a key detail: acceleration. The twin on the ship must turn around to come back. That means they change direction. That change breaks the symmetry. The twin on Earth stays in the same place the whole time and never speeds up or slows down. But the traveling twin does. They accelerate to leave Earth, decelerate to stop, turn around, then accelerate again to come back. This change of motion matters. In physics, acceleration means a change in velocity. When someone accelerates, they feel it. It's not relative, it has a physical effect. So the two twins are not in the same situation after all. Special relativity works when things move at constant speeds. But to fully explain the twin paradox, you need to bring in general relativity, which covers acceleration. In that theory, acceleration and gravity can affect time. A person who experiences more acceleration will feel less time pass compared to someone who doesn't. That's what happens with the traveling twin. This is not just theory, it's been tested many times. In one experiment, scientists put very precise atomic clocks on airplanes. When the planes returned to the ground, their clocks were slightly behind the ones that stayed on Earth. The difference matched what relativity predicted. Other experiments with satellites, like the ones used for GPS, also show this effect. GPS satellites orbit the Earth and move fast. Their clocks run slightly differently from clocks on the ground. Engineers have to adjust for this to make sure GPS stays accurate. These results match what the twin paradox describes. Time really does move slower for people who travel at high speeds. The effect is small at everyday speeds, but it becomes big when speeds get close to the speed of light. For astronauts on the International Space Station, the difference is tiny, just a few milliseconds over 6 months. But if someone traveled through space at near light speed for several years, the gap could be huge. They might come back to find that everyone they knew has aged decades, while they have aged only a few years. Let's try to make this clearer with a step-by-step example. Suppose the twin on the ship travels to a star that is 10 light years away. They travel at 99.5% the speed of light. For the person on Earth, the trip to the star and back would take about 20 years. But for the traveler, time moves slower because of time dilation. They only experience about 3 years on the ship. So when the twins reunite, the one who stayed on Earth is 20 years older, and the traveler is only 3 years older. This matches what relativity predicts. To explain why this happens, scientists use something called a space-time diagram. On this diagram, time is one axis and space is another. The path an object takes through space and time is called its world line. The twin on Earth has a straight world line. Time passes steadily. The traveling twin has a bent world line. They go out, stop, and return. That shape makes their path through time shorter. It's not about speed alone, it's about the whole journey through space-time. The more curved the path, a less time is experienced. This idea is also supported by how light behaves. In relativity, the speed of light is always the same. No matter how fast you move, light moves at the same speed. That forces time and space to stretch and shrink to keep light's speed constant. When you move fast, space seems shorter and time seems slower. This effect is not something you can feel or see while moving, but it becomes clear when you compare clocks later. So the twin paradox isn't really a paradox at all. It's a result of how time and motion work when speeds get high. The key is to remember that not all motion is equal. The twin who turns around and comes back experiences acceleration and deceleration. That changes their experience of time. The twin who stays on Earth does not accelerate and stays in one frame of reference. Because of that, more time passes for them. This also means that time is not absolute. It depends on your motion and position. Two people can experience different amounts of time between the same events, depending on how they move. That idea may feel strange, but it is part of how the universe works. We see it in experiments, and it helps explain how satellites, particles, and light behave. The twin paradox shows that time is not a fixed flow that moves the same for everyone. It can bend, stretch, and slow down. What seems like a strange science fiction story turns out to be a real and measurable part of nature. The traveler doesn't cheat time, they just follow a different path through it. The paradox of the unexpected hanging starts with a simple story. A judge tells a prisoner, "You will be hanged next week on one weekday, but the execution will come as a surprise. You won't know the day until the hangman comes for you." The prisoner begins to think it through. He wants to figure out which day it could happen. He wants to beat the surprise. He starts by thinking about Friday. If the hanging hasn't happened by Thursday night, then it must be Friday. If he knows it's coming Friday, then it's no longer a surprise. That breaks the rule. So the prisoner decides it cannot be Friday. Then he moves to Thursday. If the hanging hasn't happened by Wednesday night, and he already ruled out Friday, then Thursday is the only day left. But again, that would not be a surprise, so it cannot be Thursday either. He keeps working backward like this. He reasons that if the hanging can't be on Friday or Thursday, then Wednesday must be ruled out next. Using the same logic, he removes Tuesday and Monday too. By Sunday night, he's convinced that the hanging cannot happen at all. Every day has been ruled out because if it were on any of them, it would not be a surprise. But then Monday morning comes, and the hangman arrives. The prisoner is shocked. He wasn't expecting it. The execution happens, and it is a surprise, just as the judge said. That's the paradox. The prisoner used logic to prove the hanging could not happen, but it did happen. Worse, it happened in exactly the way he was told, on a weekday, and as a surprise. This story creates a strange loop between logic, knowledge, and belief. The prisoner's reasoning sounds solid. He rules out each day based on what he would know if the hanging hadn't happened yet. He uses backward induction, a common method in reasoning and planning. But the result doesn't match reality. His logic doesn't protect him. It fails to match how knowledge actually works. One way to explain this is through epistemic logic. This is a field that studies how knowledge, belief, and information behave. It helps us understand what it means to know something or to expect it. In this paradox, the prisoner confuses knowing something with expecting it. These are not the same. Expectation is more than just knowing what will happen. It includes timing, context, and mental readiness. For the judge's statement to hold, the hanging must come as a surprise, not because it's logically impossible to guess the day, but because in real life, the prisoner won't succeed in predicting it. The moment he thinks he has removed all options, the hangman still has a chance to act. In this case, the surprise lies not in the logical structure, but in the prisoner's belief system. He expects logic to control the outcome. But real-world events don't always follow perfect logic, especially when that logic loops back on itself. His mistake was thinking that knowing the rules would let him escape the consequences. He used logic to erase the possibility of the hanging altogether, but the rule never promised that it could be avoided, only that it would be unexpected. To see this more clearly, imagine a similar case. A teacher tells a class, there will be a surprise test next week. The students try to predict the day. They rule out Friday, because if it hasn't happened by Thursday, they'll expect it on Friday. Then they rule out Thursday using the same method. Eventually, they convince themselves there will be no test, but then the teacher gives it on Tuesday. The students are caught off guard. The test is a surprise. So the teacher's statement holds true, even though the students' logic told them it couldn't happen. The real issue here is that the statement creates a loop. It says something will happen, but only under the condition that it isn't expected. That condition depends on the mental state of the person hearing it. The moment the prisoner or the student believes they've solved it, they lose the ability to see the outcome coming. That's when the surprise happens. This kind of paradox plays with the boundary between logic and psychology. In strict logic, each step of the prisoner's reasoning seems fine, but it leads to an absurd result. It tells him that the hanging cannot happen at all. Yet the hanging does happen. The logic is sound in form, but flawed in context. It fails to handle how knowledge changes over time. Here's another way to think about it. Suppose a person says, you will receive a phone call one day next week, but you will not expect it. You might spend all week trying to guess when it will happen. You might even use the same backward logic to rule out each day. But if the call comes on Tuesday, and you had already ruled out Tuesday, then you'll be surprised. The paradox works because people confuse the process of guessing with the experience of surprise. This also shows why some statements don't fit well into formal systems. The judge's promise depends on how the prisoner thinks. It's not a fixed rule like in mathematics. It bends with belief. That makes it hard to predict. It also makes it powerful. The execution becomes inevitable and surprising, not despite the logic, but because of how the prisoner misuses logic. In philosophy, this paradox points to deeper questions. Can we truly know something that is defined by our not knowing it? Can a rule be enforced if it depends on mental state? These are not just riddles. They affect how we understand belief, expectation, and control. In law, education, and even technology, knowing how people process information is just as important as the information itself. The unexpected hanging paradox also shows how knowledge can collapse on itself. The prisoner tries to know too much. In trying to outthink the judge, he removes all possibilities. But that only blinds him. When the event finally happens, it catches him off guard. Not because it was hidden, but because his logic told him it was impossible. That's the heart of the paradox. Believing you've ruled out all options doesn't mean reality will agree. This puzzle teaches a hard truth. Perfect logic doesn't always match human experience. Sometimes the limits of knowledge are not in the world, but in how we think. The prisoner isn't wrong in his steps. He's wrong in his expectations. He treats knowledge like a lock to pick. But the judge's promise doesn't work like that. It's not a trap with an answer. It's a statement that shifts as you try to hold it still. In the end, the hanging happens not because logic failed, but because logic couldn't catch the surprise. The Soreitz paradox begins with a simple question about a heap of sand. Suppose you have a large pile, 1,000 grains, for example. That's clearly a heap. Now remove one grain. You still have a heap. Remove another grain, and so on. At what exact point does the heap stop being a heap? If you remove one grain at a time, each single removal doesn't seem to make a difference. But if you keep going, eventually you're left with one grain, and one grain is clearly not a heap. So where did the heap go? This creates a problem because the word heap doesn't have a fixed boundary. It's a vague term. We use it in daily language, and everyone understands what it means in general. But when we try to pin it down with precision, the concept falls apart. That's what makes it a paradox. If removing one grain never makes a difference, then no number of single removals should ever turn the heap into something that's not a heap. But we know that can't be true. This paradox doesn't just apply to sand. You can see it in many other places. Take a person with a full head of hair. Lose one hair, no one says you're bald. Lose another, still not bald. But at some point, the loss adds up and the person becomes bald. Yet we can't agree on the exact number of hairs that makes someone bald. The same goes for a crowd of people. If a stadium holds 10,000 people, we say it's crowded. Remove one person, still crowded. Keep removing people. At some point, the crowd becomes a small group, but the transition has no clear line. This puzzle is not about sand or hair or crowds. It's about how we use language and how we deal with categories that don't have sharp edges. In logic and philosophy, this kind of problem is called a vagueness paradox. Soreitz paradox is one of the most famous examples. One response to the paradox comes from a field called fuzzy logic. Unlike traditional logic, which only allows something to be either true or false, fuzzy logic allows for degrees of truth. In fuzzy logic, a heap is not something you either have or don't. Instead, it's something you can have more or less of. 1,000 grains might count as heap equals 1 or 100% heap. As you remove grains, the heap value slowly drops. 900 grains might be heap equals 0.9 or 90% heap. When you get down to 10 grains, maybe you're at heap equals 0.01. 1 grain would be heap equals 0. This lets us talk about heaps in a more flexible way. We don't need to find a sharp cutoff. We can accept that some things are partly heaps and partly not. This kind of approach matches how people think in real life. Our concepts often work on a sliding scale. Words like tall, rich, young, or old don't have exact definitions that apply in every case. Someone who is 5'11" might be considered tall in one country and average in another. A person with $1 million might be rich to one person, but not to another. These are not errors in language. They're part of how language works in a world full of variety and difference. Another way to approach the Soreitz paradox is through a view called supervaluationism. This idea says that when a term is vague, there can be cases where it's not clearly true or false. The truth value becomes indeterminate. This is different from saying it's both true and false, or somewhere in between. It means we just don't have a clear answer. In the context of the heap, there are many acceptable ways to draw the line between heap and not heap. Some people might say 500 grains is still a heap, while others might say it isn't. Both are valid under different interpretations. In supervaluationism, a statement is super true if it is true under all precise versions of the vague term. It is super false if it is false under all versions. If it's true in some and false in others, then it has no clear truth value. This helps us deal with the Sorites paradox because it accepts the idea that language has gray areas, instead of trying to force a precise answer where one doesn't exist. It allows for uncertainty in borderline cases. This matches how people use language in the real world. Most people don't demand an exact number of grains to define a heap. They use the word in a flexible way and adjust based on context. You can see this in legal systems as well. Laws often use vague terms like reasonable, excessive, or public. Judges and lawyers work with these terms in context. They don't try to define them down to a number. Instead, they use examples, comparisons, and judgment to apply the law in specific situations. The law understands that not every term can be made precise without losing meaning. Some philosophers try to solve the Sorites paradox by rejecting the idea that no single grain can make a difference. They say that at some point, removing one grain does change the status of the heap. It may be a sudden change, or it may be arbitrary, but it happens. This view is called the epistemic approach. It says that there is a precise point where the heap stops being a heap. We just don't know where that point is. The vagueness lies in our knowledge, not in the concept itself. This keeps traditional logic intact, but it feels less natural to most people. It doesn't match how we use language or how we think about categories that shift slowly. Other responses suggest that the problem is in how we structure the argument. The Sorites paradox assumes that if one grain doesn't make a difference, then no number of grains ever will. But this may be a flawed assumption. Small changes can build up to big differences. In real life, we see this all the time. One drop of water doesn't make you wet, but enough drops will. One step doesn't take you far, but 1,000 steps can take you miles. This is called a Sorite series, a chain of small steps that when added up lead to a large change. The mistake is in thinking that just because no step is noticeable, the total change must be unnoticeable too. In the end, the Sorites paradox teaches us something important about language and categories. Many of our everyday words are vague. They work well for communication, but they don't always hold up under strict logical tests. When we try to apply rigid logic to soft boundaries, we run into problems. That doesn't mean our language is broken. It means we need better tools to deal with gradual change and vague terms. Fuzzy logic and supervaluationism offer two such tools. They let us think more clearly about ideas that don't have sharp lines, and they show that not every puzzle needs a single clear answer to make sense. Russell's paradox begins with a question about sets. In simple terms, a set is just a collection of things. It could be a group of numbers, people, books, or anything else. In early mathematics, people believed that any clear condition could define a set. So if you could describe what goes into the set, then the set existed. That idea seems harmless, but it leads to a serious problem. Bertrand Russell pointed out the issue with one clever example. Think about the set of all sets that do not contain themselves. Most sets don't contain themselves. For example, the set of cats doesn't contain the set of cats, it contains cats. The set of books doesn't contain itself, it contains books. So these sets do not contain themselves. Now, let's collect all these kinds of sets into one big set. Call it R. R is the set of all sets that do not contain themselves. Now ask, does R contain itself? If it does contain itself, then by definition, it must not contain itself, because it only includes sets that do not contain themselves. But if it does not contain itself, then it fits the condition for inclusion, so it should contain itself. That creates a contradiction. R both does and does not contain itself. That makes no sense. This problem shook the foundations of mathematics. At the time, many people believed that math could be built entirely on logic, using simple rules and definitions. The idea was to avoid all confusion by making math as clear as possible. But Russell's paradox showed that even basic ideas like sets could lead to contradictions. To understand why this is a big deal, imagine a library. Suppose the librarian wants to create a list of all books that do not list themselves. Some books have an index or appendix that mentions themselves. Others don't. The librarian makes a list of all books that don't mention themselves. Now, should that list include itself? If it does, then it mentions itself and breaks the rule. If it doesn't, then it fits the rule and should include itself. This is the same kind of loop Russell described. Another version of the paradox uses a barber. The barber shaves all and only those men in town who do not shave themselves. So who shaves the barber? If he shaves himself, then he must not shave himself. If he doesn't shave himself, then he must shave himself. Again, a contradiction. These problems all come from self-reference. When a rule includes itself as part of what it describes, strange things happen. Most of the time, language and logic avoid this by using outside observers or separate systems. But in set theory, self-reference was built in. That's what made Russell's paradox so powerful. Mathematicians realized they needed to change the rules. They couldn't allow just any condition to define a set. There had to be limits. That's where formal set theory comes in, especially a system called Zermelo-Fraenkel set theory, often written as ZF or ZFC when the axiom of choice is included. This new system includes strict rules for how sets are built. One key rule is called the axiom of separation. It says you can only form subsets from sets that already exist. You can't just grab all objects that meet a condition. You have to start with a known set and filter from there. This stops you from creating something like the set of all sets that do not contain themselves. There's no universal set in ZF theory. You can't make a set of everything. That sounds strange at first, but it keeps the system consistent. Without this limit, contradictions like Russell's can appear again. You can think of it like building a house. If you follow clear steps and use only approved parts, the structure holds. But if you allow any part to be used in any way, you might build something that collapses. Russell showed that naive set theory, the earlier way of thinking, had too few rules. It was like building without a plan. ZF theory added structure to prevent collapse. Russell's paradox also helped shape ideas about language and logic. It showed that even small loops in definitions can cause big problems. Later thinkers like Alfred Tarski worked on ways to handle self-reference. He suggested using different levels of language. For example, you can talk about sentences in a higher-level system, but you can't let a sentence talk about its own truth directly. This avoids loops like, "This sentence is false," which cause similar problems. In computer science, the same issue comes up with recursive programs. If a program calls itself without a clear endpoint, it can crash. To prevent that, programmers set limits on how many times a function can call itself. This is the same idea: avoid uncontrolled self-reference. Russell's discovery had another effect. It forced philosophers and mathematicians to look more closely at foundations. They started asking deeper questions. What is a number? What is a function? What counts as a proof? This led to new fields like mathematical logic, model theory, and proof theory. People like Kurt Gödel, who followed after Russell, showed that even with strong rules, some truths in math can never be proven within the system itself. That built on the kind of thinking Russell helped start. Even today, Russell's paradox matters. It reminds us that not everything that sounds reasonable can be used safely in logic. You can't always trust simple ideas unless they're tested carefully. A harmless-looking definition, like the set of all sets that do not contain themselves, can bring down an entire system. This paradox also shows the power of asking the right question. Russell didn't invent new numbers or shapes. He just asked what seemed like an innocent question about sets, but the answer broke the rules people thought were solid. That's the mark of a deep idea. It changes what counts as a safe path in thought. By forcing math to clean up its definitions, Russell's paradox helped build the modern structure of logic. It's why math is more precise today. It's also why computer languages, formal proofs, and logical systems include checks and balances. They've learned from the trap that Russell revealed over 100 years ago. In the end, the paradox doesn't just challenge what we know. It changes how we think about knowing. It teaches that clarity, structure, and limits are not weaknesses in logic. They are what make logic strong. Without them, even the simplest question can unravel everything. The bootstrap paradox begins with a simple idea. Suppose a person travels back in time with a book in hand, a novel, for example. They give the book to someone in the past. That person then publishes it. Over time, the book becomes famous. It passes through generations, and eventually, the time traveler finds it again in the future. Later, they use the same book to travel back and repeat the cycle. The question is, who wrote the book? It seems like the book has no origin. No one created it in the usual way. It just exists, passed along in a loop. It was never truly written, only copied and carried. This is the bootstrap paradox. It gets its name from the idea of lifting yourself by your own bootstraps, which is impossible. The paradox shows a similar kind of problem. An object or idea exists without a clear cause. It pulls itself into existence with no beginning. This paradox is not limited to books. Imagine a musician who learns a song from a traveler. Years later, the musician records it. That recording survives, and the traveler hears it in the future. Then they bring the song back in time and play it for the musician. Where did the song come from? It seems like no one composed it. It entered time as a loop, without a creator. At the heart of the bootstrap paradox is the idea of a causal loop. This is when a sequence of events loops back into itself, with cause and effect forming a circle. One event causes the next, and eventually, the last event causes the first. The loop closes perfectly, but it raises questions about where the loop began. Normally, events have a chain of causes. A leads to B leads to C, and so on. You can trace things back to their source. A tree grows because a seed was planted. The seed came from another tree. But in a causal loop, that trace breaks down. You end up with something that seems to exist just because it exists. Some theories in physics allow for causal loops. The Novikov self-consistency principle is one of them. It says that if time travel is possible, then the timeline must be consistent. You can't change the past in a way that creates contradictions. If you go back in time, your actions must fit into history. That means a causal loop is allowed if it holds together logically. So if the book appears in the past, then it must always have appeared in the past. No one wrote it. It was always part of the timeline. This kind of loop is strange, but not impossible under some interpretations of time travel. The key idea is that cause and effect still work, but in a circular way. Each part of the loop is caused by the part before it. The future affects the past, and the past affects the future. But there is no first cause. That's what makes it feel paradoxical. In philosophy, this raises questions about information and creation. If the book was never written, does it really have an author? If a machine is invented in this kind of loop, who invented it? Did the idea come from nowhere? These are hard questions because our everyday thinking depends on clear beginnings. We expect things to start somewhere. We look for sources. The bootstrap paradox breaks that habit. You can also think of this paradox using objects. Suppose someone brings back a watch from the future and gives it to their younger self. That younger version keeps the watch, grows older, and eventually travels back to give the watch to their younger self again. The watch never breaks, never wears out, and never leaves the loop. Where was it made? Who manufactured it? No one. It just exists, always part of the cycle. In theory, this could happen forever. The object doesn't age or degrade. It just keeps moving through time in a circle. This leads to questions about the laws of physics. In the real world, objects wear down, books decay, machines break, entropy increases. So an eternal loop might not work for physical things. But the paradox still makes sense when applied to information, ideas, or small, well-preserved items. A phrase, a song, or a design can survive if passed along carefully. Some people try to explain the paradox by saying that the time traveler was always meant to go back. The book was always meant to appear. That makes the loop part of a fixed timeline. There's no contradiction because everything fits. But that doesn't solve the mystery of where the content came from. It avoids the contradiction, but not the weirdness. Other views say that such loops are not possible. They argue that something cannot exist without a source. According to this view, if time travel were real, it would have to prevent loops like this. There would need to be a rule that blocks information from forming a closed circle. Maybe time travel only works one way, or only to timelines that split off. These views try to protect the idea that everything must have an origin. There's also a view from quantum physics. Some interpretations of quantum theory suggest that time may not be as simple as it looks. In the quantum world, particles don't always follow clear paths. Events can happen in odd orders. Some theories even allow for backward influence, where a future event affects a past one. In these frameworks, a causal loop might make sense. The information is not created, it's just part of how the system works. Science fiction has used the bootstrap paradox in many stories. A character brings back a tool, idea, or identity from the future, and it becomes part of the past. In one story, a person finds a book with instructions for building a time machine. They follow the instructions, travel back, and give the book to their younger self. The book has no true author. It exists only in the loop. This kind of story works because it feels both logical and surreal. Everything lines up, but the origin is missing. That creates tension. It's not a contradiction in the strict sense, but it breaks our sense of how things are supposed to work. The loop has no beginning, and that's what makes it a paradox. The bootstrap paradox doesn't break the rules of logic. Each step in the loop makes sense. But when you look at the loop as a whole, you can't find a start. That's what makes it feel impossible, even though it holds together. It shows that time travel, if real, might not just change history, it could change how history works. It could allow objects, ideas, or information to exist without ever being made in the normal way. That doesn't mean they came from nothing. It means they came from the future, and that future only exists because the past included them. The loop closes, and nothing escapes. The lottery paradox starts with a simple case. Imagine a fair lottery with 1 million tickets. Only one ticket will win. You know this. The rules are clear, and the drawing is random. Now pick a ticket. Say, ticket number 487231. Is it reasonable to believe that this ticket will lose? Yes. The chance of it winning is 1 in a million. That means it's very likely to lose. In fact, it seems reasonable to believe that any given ticket will not win. So far, everything seems fine. You can look at any ticket and say, this one won't win, and you're probably right. But now consider all 1 million tickets together. If you believe that each one will lose, then you must also believe that no ticket will win. That's the contradiction. You know that one ticket will win. The rules guarantee it. Yet, if you believe each individual ticket will lose, then you end up believing that none of them will win. That is clearly false. This is the lottery paradox. It shows a problem with how belief works when tied to probability. Each individual belief makes sense, but when you put them all together, they lead to something false. The issue isn't about the lottery itself. The rules of the game are fine. The problem lies in what it means to believe something, and how strong a belief must be to count as rational. One way to understand the paradox is through the idea of high probability. When something is very likely, like a ticket losing, you may feel confident in believing it. But confidence based on probability is not the same as certainty. A 1 in a million chance is tiny, but it's not zero. So while it's very likely that a ticket will lose, it's not guaranteed. Treating high probability as if it means certainty is where the mistake begins. You can see this in everyday life. Suppose you order a package online. The tracking says it will arrive today. Based on past deliveries, you believe it will show up, but there's still a chance that it won't. Traffic, weather, or a lost label could delay it. You have a good reason to expect it, but not enough reason to be certain. If someone asks you whether it will arrive, you might say yes, but you know there's a small chance you'll be wrong. That's similar to believing a ticket will lose. The belief is strong, but not airtight. Now imagine applying this kind of belief to every ticket in the lottery. You believe ticket 1 will lose. You believe ticket 2 will lose. You go on like this up to ticket 1,000 tickets. Each belief is supported by strong odds, but taken together, they contradict what you know to be true, that one ticket must win. So something has gone wrong in the logic of belief. This leads to deeper questions in epistemology, the study of knowledge and belief. One big question is, when is it okay to believe something? Is it enough that a claim is very likely to be true? Or do you need more than that, like evidence that rules out all doubt? Some thinkers argue that belief should only apply to things that are certain or very close to certain. That would mean you can't rationally believe that a single ticket will lose. You can say it's very likely, or you can bet on it, but you can't believe it in the strict sense. You can only believe things that won't lead to contradiction when combined with other beliefs. Other thinkers suggest that belief can come in degrees. Instead of saying, "I believe this ticket will lose," you say, "I believe it will lose with 99.9999% confidence." This approach avoids treating beliefs as all or nothing. It matches how people think in real situations. We often act on high confidence, even if we're not completely sure. But that leads to another problem. If belief comes in degrees, then what counts as a belief at all? Is there a threshold where confidence becomes belief? If so, where is that line? Is it 90%? 95%? And how do we handle cases where many weak beliefs add up to something false? The lottery paradox shows that belief doesn't always behave the way logic expects. In logic, if you believe A and you believe B, and A and B together imply C, then you should also believe C. That rule is called deductive closure. But in the lottery case, believing each ticket will lose and believing that only one will win leads to a contradiction. So either we give up deductive closure or we adjust how belief works. Some responses to the paradox suggest that belief should not be closed under deduction in every case. That means it's possible to believe many things that are individually likely without being forced to believe what they logically imply. This sounds odd, but it matches how people often think. You might believe each of your coworkers is unlikely to win the office raffle, but you don't believe that no one will win. You accept the risk that your beliefs are limited in scope and not logically complete. Another view says that belief and knowledge are different. You can believe that a ticket will lose, but you don't know it will lose. Knowledge requires more than high probability. It needs evidence that removes serious doubt, so you might act on your belief, but still admit that it could turn out wrong. In this way, belief becomes a practical tool, not a claim of certainty. This difference shows up in legal systems. Jurors are told to convict only when they believe the accused is guilty beyond a reasonable doubt. That's not the same as absolute certainty. It allows for belief based on high probability, while still recognizing that mistakes can happen. In civil cases, the standard is even lower, just a preponderance of evidence, or more likely than not. These standards show that belief in real life often works on probabilities, not guarantees. The lottery paradox forces us to ask what we mean when we say, "I believe." Is it a commitment to truth? A mental habit based on odds? A signal to act a certain way? Depending on the answer, we may have to rethink how we treat belief in uncertain situations. The paradox also highlights the risk of treating many small, rational beliefs as if they automatically add up to a rational whole. Logic expects beliefs to connect neatly, but in real thinking, beliefs are often loose and local. They serve immediate decisions, not complete systems. When we try to force them into full logical closure, we find trouble. The lesson of the lottery paradox is not just about games or tickets. It's about how people handle uncertainty. We live in a world where outcomes are often unclear, and most decisions involve risk. The paradox shows that it's easy to slip from very likely to definitely, and that doing so can lead to problems, even if every step seems right on its own. Belief, like probability, needs care when scaled across many cases, and sometimes the structure of our thinking needs more than logic to stay consistent. Newcomb's paradox asks a simple question: should you take one box or two? But hidden in that choice is a conflict between two ways of thinking about decision-making. The setup goes like this. There are two boxes on a table. Box A is transparent and always contains $1,000. Box B is opaque. It either contains $1 million or nothing. A powerful predictor, known for making accurate predictions, has already filled the boxes based on what it thinks you will do. If the predictor believes you will take only box B, it puts $1 million in it. If it believes you will take both boxes, it leaves box B empty. You now face the choice. You can take only box B, or you can take both. The predictor has already made its move. The money is already in the boxes. What should you do? At first glance, it seems obvious. The money is already there. If box B has $1 million, then taking both gets you $1 million and $1,000. If box B is empty, then taking both still gives you $1,000. Either way, taking both boxes gives you more money than taking just one. This is the argument from dominance. You should take both because it gives you at least as much money in every case, and possibly more. But there's a second way to look at it. You know the predictor is almost always right. If you take both boxes, the predictor likely expected that and left box B empty. If you take only box B, the predictor probably expected that and filled it with $1 million. So if you want to end up with the million, the best choice is to take only box B. This is the argument from expected value. If the predictor is right 99% of the time, then one boxing gives you a 99% chance at $1 million. Two boxing gives you a 99% chance at only $1,000. So the higher payoff comes from one boxing. Now you have two arguments pulling in opposite directions. The dominance argument says take both. The expected value argument says take one. They can't both be right. Which one should you follow? This is where decision theory comes in. There are two main types: causal decision theory, CDT, and evidential decision theory, EDT. CDT says you should choose based on what your action causes. Your choice can't affect the past. The money is already in the boxes. Newcomb's paradox asks a simple question: should you take one box or two? But hidden in that choice is a conflict between two ways of thinking about decision-making. The setup goes like this. There are two boxes on a table. Box A is transparent and always contains $1,000. Box B is opaque. It either contains $1 million or nothing. A powerful predictor, known for making accurate predictions, has already filled the boxes based on what it thinks you will do. If the predictor believes you will take only box B, it puts $1 million in it. If it believes you will take both boxes, it leaves box B empty. You now face the choice. You can take only box B, or you can take both. The predictor has already made its move. The money is already in the boxes. What should you do? At first glance, it seems obvious. The money is already there. If box B has $1 million, then taking both gets you $1 million and $1,000. If box B is empty, then taking both still gives you $1,000. Either way, taking both boxes gives you more money than taking just one. This is the argument from dominance. You should take both because it gives you at least as much money in every case, and possibly more. But there's a second way to look at it. You know the predictor is almost always right. If you take both boxes, the predictor likely expected that and left box B empty. If you take only box B, the predictor probably expected that and filled it with $1 million. So if you want to end up with the million, the best choice is to take only box B. This is the argument from expected value. If the predictor is right 99% of the time, then one boxing gives you a 99% chance at $1 million. Two boxing gives you a 99% chance at only $1,000. So the higher payoff comes from one boxing. Now you have two arguments pulling in opposite directions. The dominance argument says take both. The expected value argument says take one. They can't both be right. Which one should you follow? This is where decision theory comes in. There are two main types: causal decision theory, CDT, and evidential decision theory, EDT. CDT says you should choose based on what your action causes. Your choice can't affect the past. The money is already in the boxes, so your choice can't change what's inside. Under CDT, taking both boxes is the rational move. EDT says you should choose based on what your choice tells you about the world. Your decision is evidence of what has likely already happened. If you choose one box, it suggests the predictor expected that and put the money in. If you choose both, it suggests the predictor expected that and left the box empty. So under EDT, one boxing is the rational move. To see the conflict more clearly, imagine the predictor has watched thousands of people make this choice. It has learned patterns. Almost everyone who chose one box ended up with $1 million. Almost everyone who chose both ended up with $1,000. That's the data. So when you walk in and consider your choice, you know what's likely to happen. Choosing one box usually leads to more money. That's the outcome you want. But at the same time, you know the money is already in the boxes. Your choice now can't change what's inside. That's the trap. Your action feels both free and predicted. Some people solve the paradox by saying the predictor can't really be that accurate. No one can know the future with certainty, but that avoids the paradox instead of solving it. The puzzle assumes the predictor is reliable. Not perfect, just very, very good. Good enough that your choice gives strong evidence about what's already in the boxes. Others try to solve the paradox by questioning free will. If your decision is already predicted, then maybe it's not really a free choice. Maybe you're just playing out a script. But even if your choice is part of a pattern, it still feels like a choice. You can think about it, weigh your options, and pick one. The paradox doesn't need to deny free will. It only needs you to accept that the predictor's guess is probably right. One way to test this is to run a thought experiment. Imagine the predictor has run 1,000 trials before you. In every case, it made its prediction and filled the boxes. The results match the pattern. One boxers get $1 million. Two boxers get $1,000. Now your Moore's paradox begins with a strange kind of sentence. It's raining, but I don't believe it is. There's no contradiction in logic. The sentence isn't false by definition. It's possible that it is raining outside and that the speaker doesn't believe it. Both claims can be true, but saying them together feels off. The sentence seems wrong, even though it isn't logically broken. That's what makes it a paradox. It shows how language, belief, and communication can clash, even when logic stays intact. The paradox was introduced by philosopher G.E. Moore in the early 20th century. He noticed that some statements feel irrational, not because they're false, but because they go against the way we expect people to talk about their own beliefs. If you hear someone say, "It's raining, but I don't believe it is," you don't just think they're wrong. You think they're confused. You wonder how they can assert something while also saying they don't believe it. This is not a problem of truth or falsehood. It's a problem of expression. The sentence is pragmatically inconsistent. That means it doesn't break any rules of logic or grammar, but it breaks the rules of normal speech and belief. When you say it's raining, you're making a claim about the world. You're telling your listener that you believe it's true. That's part of what it means to say something. We expect speakers to mean what they say. So when someone says it's raining, we assume they believe it. When they immediately add, "but I don't believe it is," they cancel that assumption. They break the expectation they just created. This makes the sentence feel unstable. The first part tells us one thing. The second part takes it back, not by denying the rain, but by denying belief in the rain. That creates tension. The speaker sounds unreliable, not because the statement is false, but because it doesn't fit with how belief works in communication. You can compare this to saying, "I am asleep right now." That's not a contradiction either, but it's not something you can say sincerely while awake and talking. The act of saying it shows that it's false. It fails not because of logic, but because of context. Moore's sentence fails in the same way. Saying, "I don't believe it's raining," right after "it's raining," makes the whole statement fall apart at the level of trust. This idea shows how language carries more than just content. It carries commitment. When you say something, Moore's paradox begins with a strange kind of sentence. "It's raining, but I don't believe it is." There's no contradiction in logic. The sentence isn't false by definition. It's possible that it is raining outside and that the speaker doesn't believe it. Both claims can be true, but saying them together feels off. The sentence seems wrong, even though it isn't logically broken. That's what makes it a paradox. It shows how language, belief, and communication can clash, even when logic stays intact. The paradox was introduced by philosopher G.E. Moore in the early 20th century. He noticed that some statements feel irrational, not because they're false, but because they go against the way we expect people to talk about their own beliefs. If you hear someone say, "It's raining, but I don't believe it is," you don't just think they're wrong. You think they're confused. You wonder how they can assert something while also saying they don't believe it. This is not a problem of truth or falsehood. It's a problem of expression. The sentence is pragmatically inconsistent. That means it doesn't break any rules of logic or grammar, but it breaks the rules of normal speech and belief. When you say "it's raining," you're making a claim about the world. You're telling your listener that you believe it's true. That's part of what it means to say something. We expect speakers to mean what they say. So when someone says, "It's raining," we assume they believe it. When they immediately add, "but I don't believe it is," they cancel that assumption. They break the expectation they just created. This makes the sentence feel unstable. The first part tells us one thing. The second part takes it back, not by denying the rain, but by denying belief in the rain. That creates tension. The speaker sounds unreliable, not because the statement is false, but because it doesn't fit with how belief works in communication. You can compare this to saying, "I am asleep right now." That's not a contradiction either, but it's not something you can say sincerely while awake and talking. The act of saying it shows that it's false. It fails not because of logic, but because of context. Moore's sentence fails in the same way. Saying, "I don't believe it's raining," right after "it's raining," makes the whole statement fall apart at the level of trust. This idea shows how language carries more than just content. It carries commitment. When you say something, you commit to believing it, or at least acting like you do. If you say, "I left my keys on the table," and then say, "but I don't believe that," people won't know what to make of it. They'll wonder why you said it at all. Your statement becomes useless for guiding action or understanding. In philosophy, this leads to questions about belief and knowledge. When you assert something, do you always express belief? Some thinkers say yes. To assert something is to put your belief into words. Others say no. You can assert something for other reasons, like playing devil's advocate or quoting someone else. But in ordinary speech, most people link assertions with belief. That's why Moore's sentence feels off. It breaks that link. This paradox also matters for understanding self-knowledge. Most people assume they know what they believe. If you say, "It's raining," and someone asks, "Do you believe that?" you'd likely say yes. But Moore's sentence shows that this link can break. You can say something true about the world while saying something false or confused about your own mind. That raises questions. Can you be wrong about what you believe? Can belief and knowledge pull apart? Imagine a person reading a weather report. The report says it's raining. They trust the source, so they say it's raining. But deep down, they still feel unsure. Maybe the sky looks clear. Maybe the report has been wrong before. They speak the words, but hold back belief. In that case, "It's raining, but I don't believe it is," describes their state. It's odd, but it might be honest. Or think about someone who's in denial. Their friend says something hurtful. The person tells others, "He doesn't care about me," but then adds, "I still don't really believe it." Again, both parts might be true. The paradox of tolerance, first described by philosopher Karl Popper, presents a challenge to how we think about freedom in open societies. The paradox asks this question: should a tolerant society tolerate intolerance? At first, it seems like the answer should be yes. After all, tolerance means accepting different views, even ones we dislike. But Popper argued that if we tolerate all ideas, including intolerant ones, we risk losing tolerance entirely. Intolerant groups, once accepted, may use their freedom to destroy the very system that allowed them to speak in the first place. Imagine a society that values free speech, freedom of belief, and peaceful disagreement. Now imagine a group appears in that society preaching hatred, exclusion, and the suppression of others. At first, this group is small. They use the freedom of the tolerant society to spread their ideas. They hold rallies, publish pamphlets, and recruit supporters. Over time, they grow stronger. Their speech turns into action. They begin to pressure others into silence. They target minority groups, spread fear, and call for the removal of rights. If the society continues to tolerate them without limits, eventually the intolerant group may take control. When they do, they will end freedom. They will outlaw disagreement. The society will no longer be tolerant, because the tolerant allowed intolerance to grow unchecked. This is the core of the paradox. Tolerance, if left unlimited, can destroy itself. To survive, tolerance must set boundaries. It must refuse to accept those who aim to destroy openness, diversity, or the rule of law. This doesn't mean silencing all disagreement. It doesn't mean punishing people for holding unpopular opinions. It means recognizing when certain beliefs or behaviors aim not to coexist, but to dominate or erase others. In those cases, the tolerant society must protect itself, not out of fear, but out of principle. You can compare this to a garden. You welcome many kinds of plants. Some are tall, others short. Some grow quickly, others take years. But one plant begins to strangle the rest. It spreads fast, blocks the sun, and takes all the space. If you let it grow unchecked in the name of fairness, soon you'll have nothing but that one plant. The variety will be gone. To protect the garden, you must trim or remove the plant, not because you hate it, but because you value the whole system. This paradox of tolerance, first described by philosopher Karl Popper, presents a challenge to how we think about freedom in open societies. The paradox asks this question: should a tolerant society tolerate intolerance? At first, it seems like the answer should be yes. After all, tolerance means accepting different views, even ones we dislike. But Popper argued that if we tolerate all ideas, including intolerant ones, we risk losing tolerance entirely. Intolerant groups, once accepted, may use their freedom to destroy the very system that allowed them to speak in the first place. Imagine a society that values free speech, freedom of belief, and peaceful disagreement. Now imagine a group appears in that society preaching hatred, exclusion, and the suppression of others. At first, this group is small. They use the freedom of the tolerant society to spread their ideas. They hold rallies, publish pamphlets, and recruit supporters. Over time, they grow stronger. Their speech turns into action. They begin to pressure others into silence. They target minority groups, spread fear, and call for the removal of rights. If the society continues to tolerate them without limits, eventually the intolerant group may take control. When they do, they will end freedom. They will outlaw disagreement. The society will no longer be tolerant, because the tolerant allowed intolerance to grow unchecked. This is the core of the paradox. Tolerance, if left unlimited, can destroy itself. To survive, tolerance must set boundaries. It must refuse to accept those who aim to destroy openness, diversity, or the rule of law. This doesn't mean silencing all disagreement. It doesn't mean punishing people for holding unpopular opinions. It means recognizing when certain beliefs or behaviors aim not to coexist, but to dominate or erase others. In those cases, the tolerant society must protect itself, not out of fear, but out of principle. You can compare this to a garden. You welcome many kinds of plants. Some are tall, others short. Some grow quickly, others take years. But one plant begins to strangle the rest. It spreads fast, blocks the sun, and takes all the space. If you let it grow unchecked in the name of fairness, soon you'll have nothing but that one plant. The variety will be gone. To protect the garden, you must trim or remove the plant, not because you hate it, but because you value the whole system. This example shows that tolerance is not the same as weakness. True tolerance requires strength and judgment. It requires knowing when to say, "This is too far." Not every voice deserves a platform. Not every belief deserves equal space in public life. A society that values human rights must be willing to defend them, even against those who claim the right to take them away. Popper made this argument in the context of his time. He lived through the rise of fascism in Europe. He saw how free societies failed to stop violent ideologies early on. They gave space to movements that used freedom to destroy freedom. The lesson he drew was clear. Tolerance must not mean letting anyone say or do anything. It must include the right to push back. This idea applies today. Modern democracies face challenges from groups that reject basic values, groups that call for the exclusion of others, deny facts, or seek to end debate. They may hide behind the language of free speech or personal belief, but their goal is not to join the conversation. It is to shut it down. In these cases, the paradox reminds us that freedom is not neutral. It requires action to survive. One example is hate speech. Many countries protect free expression, but also limit speech that calls for violence or dehumanization. These limits are not against freedom, they support it. They stop the rise of forces that would remove rights from others. The same applies to groups that use threats. The Raven paradox begins with a simple idea. Imagine a scientist who wants to confirm the statement, "All ravens are black." One way to test this is to look at ravens. If each raven the scientist sees is black, that supports the claim. Over time, many black ravens give more reason to think the rule is true. This seems natural. Now look at the logic of the sentence. "All ravens are black" is logically the same as "all non-black things are not ravens." These two statements have the same meaning. If something is not black, then it should not be a raven. This is just another way of saying the same thing. So if you want to confirm all ravens are black, you should also be able to confirm all non-black things are not ravens. That brings us to the strange part. Imagine someone observes a green apple. It is not black, and it is not a raven. That fits the rule. It's a non-black thing that isn't a raven. So in theory, that observation supports the claim that all ravens are black. This leads to the paradox. How can seeing a green apple give us more reason to believe that all ravens are black? It seems absurd. The apple has nothing to do with ravens. It's not the right kind of observation. Yet the logic says it confirms the rule. The paradox was first described by Carl Hempel in the 1940s. He pointed out that according to formal logic, a general rule like all ravens are black applies to both the presence of black ravens and the absence of non-black ravens. But this creates a gap between what logic says and what people feel is meaningful evidence. To understand what's going on, we need to look at how confirmation works. Not all true observations support a claim in the same way. Some carry more weight than others. Seeing a black raven matters a lot. Seeing a green apple doesn't seem to matter at all. Why is that? This is where probability helps. Instead of thinking in terms of yes or no, we can think in terms of degrees. Bayesian probability gives us a way to do this. In this system, we start with a belief, say that all ravens are black. We call this the prior belief. As we gather new data, we update that belief. We ask, how likely is this data if the rule is true? How likely is it if the rule is false? The raven paradox begins with a simple idea. Imagine a scientist who wants to confirm the statement, all ravens are black. One way to test this is to look at ravens. If each raven the scientist sees is black, that supports the claim. Over time, many black ravens give more reason to think the rule is true. This seems natural. Now look at the logic of the sentence. All ravens are black is logically the same as all non-black things are not ravens. These two statements have the same meaning. If something is not black, then it should not be a raven. This is just another way of saying the same thing. So if you want to confirm all ravens are black, you should also be able to confirm all non-black things are not ravens. That brings us to the strange part. Imagine someone observes a green apple. It is not black, and it is not a raven. That fits the rule. It's a non-black thing that isn't a raven. So in theory, that observation supports the claim that all ravens are black. This leads to the paradox. How can seeing a green apple give us more reason to believe that all ravens are black? It seems absurd. The apple has nothing to do with ravens. It's not the right kind of observation. Yet the logic says it confirms the rule. The paradox was first described by Carl Hempel in the 1940s. He pointed out that according to formal logic, a general rule like all ravens are black applies to both the presence of black ravens and the absence of non-black ravens. But this creates a gap between what logic says and what people feel is meaningful evidence. To understand what's going on, we need to look at how confirmation works. Not all true observations support a claim in the same way. Some carry more weight than others. Seeing a black raven matters a lot. Seeing a green apple doesn't seem to matter at all. Why is that? This is where probability helps. Instead of thinking in terms of yes or no, we can think in terms of degrees. Bayesian probability gives us a way to do this. In this system, we start with a belief, say that all ravens are black. We call this the prior belief. As we gather new data, we update that belief. We ask, how likely is this data if the rule is true? How likely is it if the rule is false? The answer changes our belief. That change is called the posterior belief. Now consider the green apple. If we already know that most things in the world are not ravens, then seeing a non-black thing that isn't a raven is not surprising. It doesn't change much. The data fits both the world where all ravens are black and the world where some are not. The apple doesn't help us choose between the two. It adds almost nothing to the belief. But a black raven is different. If the rule is false, if some ravens are not black, then seeing only black ravens becomes less likely over time. Each new black raven increases our confidence in the rule. That's because it narrows the gap between what we expect and what we see. To put it another way, evidence supports a claim when it makes the claim more likely than its alternatives. The green apple doesn't do that. It's expected whether the rule is true or false. But the black raven makes a difference. It supports the rule in a meaningful way. So why does the paradox appear? The answer is that logical equivalence doesn't always match confirmation strength. Two statements may be logically the same, but that doesn't mean they're confirmed in the same way. In practice, some observations matter more than others. That's where logic ends and probability begins. This helps explain why the paradox feels wrong. We trust our sense of relevance. We know that data has to be connected to the claim. If you're testing a claim about ravens, you should look at ravens. You shouldn't test a theory about birds by looking at apples. The problem comes when we confuse formal rules with practical reasoning. Think about another example. Suppose someone claims all cars in this city are blue. You want to test this. Seeing a green bicycle Buridan's ass is a thought experiment that shows a problem with decision-making when there is perfect balance. The story goes like this. A donkey stands between two identical haystacks. Both are the same distance away. Both have the same amount of food. Both look and smell the same. The donkey is hungry and wants to eat. But it can't find a reason to choose one haystack over the other. Since the options are equal, and there's no reason to prefer one, the donkey stays in place. In the story, it starves to death. The paradox seems silly at first. No real animal would starve like that. But the point isn't about donkeys. It's about how decisions are made when two choices are perfectly equal. If there's no reason to choose one thing over another, what makes a decision happen? Does it require a reason at all? Or can something act without one? The story is named after Jean Buridan, a 14th century French philosopher. He didn't actually describe the donkey, but his ideas about rational choice inspired the tale. In his view, rational agents always choose the better option. If two options are equal, there is no better choice, so the agent can't choose. That leads to inaction. The donkey becomes a symbol for any agent caught between two equal choices and unable to move. This idea connects to decision theory, which studies how choices are made. In simple models, an agent lists its options, weighs the outcomes, and picks the one with the highest value. That works well when options differ. If one haystack is bigger or closer, the donkey chooses that one. But when options have equal value, the model doesn't offer a clear next step. It's like a scale stuck at balance. There's no signal to push it one way or the other. In real life, though, decisions still happen. Animals don't starve between equal food sources. People don't freeze in place when given two matching options. Something always breaks the tie. The paradox makes us ask, what is that something? One answer is randomness. If all else is equal, a small random factor can tilt the balance. The donkey might move its head slightly and see one haystack from a better angle. A gust of wind might shift the smell of the hay. One step might bring it closer to one side. None of these are rational in the strict sense, but they still influence the outcome. Randomness doesn't follow reason, but it leads to action. Another answer comes from biology. Real organisms are not purely rational. They have instincts, habits, and limits. A hungry donkey won't calculate endlessly. Its need to eat will push it to act. It may simply pick a direction out of impatience or stress. The body acts before the mind finishes thinking. In that sense, survival depends not on perfect logic, but on the ability to act even when logic stalls. Humans do this too. Imagine someone standing in front of two vending machines that offer the same snack at the same price. If both machines are working and there's no line, they might hesitate for a moment, but they still choose. Maybe they reach with their dominant hand. Maybe they pick the machine on the side they usually stand. The decision doesn't come from deep thought. It comes from context, muscle memory, or mood. That's enough to break the tie. Decision theory includes ways to model this. Some versions add tie-breaking rules. If two options have equal value, pick one at random, or assign small hidden weights, noise, that make one slightly more attractive. These models reflect how people actually behave. They show that real agents don't need perfect reasons to act. They just need enough push to choose. The paradox also touches on free will. Some people ask, if every decision must be based on a reason, and no reason is stronger than another, does that mean we can't act freely? But that view assumes choice is always rational. In practice, choice often includes emotion, habit, and impulse. We might tell ourselves reasons afterward, but many choices come from factors we don't fully control or understand. That's not a flaw. It's how decision-making works in real systems. In computer science, similar problems arise in algorithms. A machine might be asked to choose between two equal paths. If no rule is given, the program can freeze or loop. To avoid this, programmers add random number generators or fallback rules. That way, the system keeps moving. The machine doesn't need a better reason. It just needs a way to avoid getting stuck. This is a technical fix for a philosophical problem. You can also see the paradox in voting. Suppose two candidates in an election are perfectly tied in the polls. Each has equal support. If one voter has to decide the result and sees both as equally good, what should they do? Some might flip a coin. Some might look for small differences, even if they don't matter much. Some might decide not to vote. The point is that decisions don't stop just because options are equal. People find a way forward. Buridan's ass is useful because it shows the limits of pure logic in decision-making. It reminds us that real-world choices often involve more than value. Timing, movement, background noise, and personal quirks all shape what happens. In fact, if we waited for perfect reasons every time, we'd rarely act at all. Life forces action before logic is complete. The donkey's mistake is not failing to choose. It's assuming that a perfect reason must appear before acting. That doesn't match reality. Real agents, whether animals or humans, learn to act under uncertainty. They don't always pick the best option. Sometimes they just pick one. That's not failure, that's survival. This is why decision theory includes more than rational models. It studies how people behave under pressure, how they simplify choices, and how they use patterns to avoid overload. It accepts that choice is often messy, and it sees value in action itself, even when the reasons are thin. Buridan's ass is a simple story with a deep lesson. If we wait for the perfect reason to act, we may never act at all. The world rarely offers perfect balance. When it does, our task isn't to solve it. Our task is to move anyway, because movement, even without clear cause, is often the better choice than stillness in the face of need. The two envelopes paradox starts with a simple game. You're shown two envelopes, and you're told one has twice as much money as the other. You don't know which one holds the larger amount. You choose one envelope at random, and just as you're about to open it, someone offers you a chance to switch. Now you're stuck with a decision. Should you stick with your envelope, or should you trade it for the other? At first, it feels like there's no real reason to switch. The envelopes look the same. You picked one fairly, but then a thought creeps in. What if the other envelope has more money? If you've picked the smaller amount, the other must have twice as much. But if you've picked the larger amount, then the other must be half of what you have. So now your mind starts weighing possibilities. You tell yourself, maybe there's a 50-50 chance that the other envelope has more. Maybe it's worth switching. After all, you could walk away with more than you started with. And here's where the paradox begins to twist your thinking. Because you start to believe that switching is always the better option. You imagine opening your envelope and finding, say, $100. Then you think, if this is the smaller amount, the other envelope might have 200. If this is the larger amount, the other might have only 50. Somehow, the idea of doubling your money feels stronger than the risk of cutting it in half. And once you start thinking that way, you feel like you should always switch, no matter what's in your envelope. But then something strange happens. You realize that this logic would apply even if you'd already switched. If you switch and find 200 in the second envelope, you feel like switching again, as if the first might now have 400, and suddenly you're caught in a loop. You feel the urge to switch forever. You're chasing a gain that never quite arrives. That's the heart of the paradox. What's going wrong? It turns out the problem isn't with the envelopes, it's with the way we reason about them. When you start imagining what the other envelope might hold, you're relying on guesses, not facts. You assume there's an equal chance that the money in your envelope is the smaller amount or the larger one. But that assumption doesn't hold up. You don't actually know how the amounts were chosen in the first place. This matters more than it seems. Imagine this game was set up by someone who picked a number at random, maybe $50, and then filled the envelopes with that and with twice that, 100. You're handed an envelope at random. If you're holding 50, the other envelope has more. But if you're holding 100, the other one has less. Without knowing how the amounts were chosen, you can't say whether you're holding the smaller amount or the larger one. And if you can't say that, you can't really say that switching is better. The illusion of advantage comes from treating every amount you find as a kind of middle point. You believe that no matter what number is in your envelope, the other one has an equal chance of being higher or lower. But that's not necessarily true. And without knowing the method used to fill the envelopes, you're trying to make a decision based on unknowns. The situation is like being handed a sealed envelope and told, there's a surprise inside, but if you switch, it might be better. If that offer comes with no clear rule or structure behind it, your decision starts to drift away from logic and into guesswork. And in this game, the more you try to calculate your way out of the uncertainty, the deeper into the paradox you fall. One way to understand this is to step back and think about how the game works as a whole. When you first chose an envelope, you had no reason to think it was better or worse than the other. You picked it fairly. If the game is truly balanced, if both envelopes were filled according to the same method, then switching shouldn't give you an advantage. The two envelopes are symmetrical. Whatever logic you apply after picking one, you could have applied before. And as that logic says you should switch, it also would have said you should switch back. That's the trap. But real decisions don't work like that. In actual games or in life, choices often come with background rules. Maybe the amounts were drawn from a fixed list. Maybe there was a maximum limit on the money inside. If you knew the rules, you could make a better decision. But without that information, you're making choices in the dark. The two envelopes paradox is not about greed or guessing. It's about the limits of reason when we're missing key information. It shows how easy it is to build a perfect-sounding argument on top of shaky ground. The numbers make sense in your head, but only because the foundation beneath them is unclear. In the end, the paradox isn't telling you that switching is always wrong. It's telling you that the choice only makes sense when you understand the whole setup. Without knowing how the game was built, trying to outthink it with vague probabilities won't help. The envelopes may promise more, but unless you can see the rules behind them, the smartest move might be the simplest one. Just choose and don't look back. A lottery ticket paradox begins with a simple setup. Imagine a fair lottery with 1,000,000 tickets. You know that exactly one ticket will win. Now pick any one ticket, say ticket number 123,456. You look at it and think, this one won't win. That belief seems perfectly reasonable. After all, each ticket has a 1 in a million chance. The odds that your specific ticket is the winner are incredibly low. You'd bet money against it. The same is true for any other ticket in the lottery. You'd say the same thing about ticket 1 or ticket 500,000 or ticket 999,999. Each individual ticket is almost certain to lose. Now try to apply this reasoning to the entire set of tickets. You believe that ticket 1 won't win. You also believe that ticket 2 won't win, and ticket 3, and ticket 4. If you keep going, You end up believing that none of the million tickets will win. But that conclusion is clearly false. You know that one of them will win. The lottery rules guarantee it. That's the paradox. You are led to believe something about the whole. No ticket will win. That directly conflicts with something you know. One ticket must win. Every individual belief seems rational on its own, but their combination leads to an irrational outcome. This is a problem in the theory of belief. It shows how beliefs that make sense by themselves can clash when taken together. Philosophers call this a problem of rational belief closure. That means, if you believe a set of things, and those things together imply something else, you should also believe the result. But in the lottery paradox, if you believe every single ticket will lose, then by closure, you must believe that no ticket will win. That violates what you know for sure, that the lottery has exactly one winner. So the question is, where does the reasoning go wrong? Are you wrong to believe that any single ticket will lose? Or are you wrong to combine those beliefs into a larger conclusion? The paradox doesn't give an easy answer. That's what makes it a paradox. One possible way to look at the problem is to say that it's never truly rational to believe that a given ticket will lose. You can say it's very likely to lose. You can bet that it will lose, but you shouldn't actually believe it will. The reasoning here is that belief should be reserved for things that are very close to certain. If something has a 1 in a million chance of being true, that's still a chance. You can't fully believe it's false. That helps avoid the paradox. If you don't believe that each ticket will lose, then you don't end up believing that none will win. You just think that each ticket is very unlikely to win, and you leave it at that. The conflict disappears, but this solution comes with a cost. It forces you to set a very high bar for belief. You have to say that even extremely likely things don't deserve belief. That's not how people usually talk. In ordinary life, we believe things all the time based on high probability. You might believe it won't rain tomorrow, even if there's a 5% chance. You believe your car will start. You believe your friend will show up. You don't wait for certainty. So this approach, reserving belief only for near certainties, doesn't match how people actually reason. It solves the paradox, but at the price of changing the way belief works. Another approach is to say that beliefs don't always have to be closed under logic. In other words, you can believe that ticket 1 will lose, and that ticket 2 will lose, and so on, without also believing that no ticket will win. You treat each belief as local. You don't combine them. This keeps the individual beliefs intact, but it denies that belief must always follow strict rules of deduction. That might feel strange, especially in fields like logic or math, where deduction is everything. But in daily reasoning, people often accept beliefs that don't fully line up when combined. We believe our friends are honest. We believe people make mistakes. Sometimes we believe things that are only mostly true. We live with the tension. So this second view says that belief doesn't have to behave like pure logic. It behaves more like judgment. Each belief stands on its own. The whole doesn't have to match the sum of the parts. That allows for more flexibility. It also fits with how people handle uncertainty in real life. A third way to look at the paradox is to distinguish between full belief and degrees of belief. Instead of saying, "I believe ticket 1 will lose," you say, "I believe with 99.9999% confidence that ticket 1 will lose." Now you're working with probabilities, not sharp yes or no statements. This model is used in Bayesian reasoning. In that system, beliefs aren't things you either have or don't have. They come in degrees. This helps because it avoids the logical conflict. You can say you have a high degree of belief that each ticket will lose and still maintain that you are certain one of them will win. The math works out. There's no contradiction. But this also shifts the meaning of belief. It turns belief into a number, not a commitment. In everyday language, belief usually means taking a stand. You believe something, and you act on it. Probabilities feel softer. They let you hedge. So while this approach is clean and logical, it doesn't capture how people use belief in regular conversation. Each solution fixes part of the problem, but each has a trade-off. You can tighten the rules for belief and avoid believing likely things. You can loosen the rules for closure and let beliefs coexist even when they don't add up. Or you can turn belief into a scale of confidence and treat the paradox as a math problem. No option is perfect. That's what makes it a paradox. The lottery ticket paradox shows how hard it is to balance reason and realism. Logic wants beliefs to be clean and closed. Real life fills them with guesswork, confidence, and partial knowledge. Sometimes our best reasoning still leads us into traps. That's not failure. It's a sign that belief is a more complex thing than a simple yes or no. It lives in the space between what we expect, what we know, and what we're willing to say out loud. The paradox of choice describes a situation many people face every day. It happens when having more options doesn't lead to more freedom or happiness. It leads to frustration and regret. The idea is simple. When you have too many choices, making a decision becomes harder, not easier. And even after you decide, you're more likely to feel unhappy about it. This goes against what many people assume. We often think that more choice means more freedom, and that freedom should always be good. But in practice, too much choice can do more harm than good. Imagine walking into a store to buy a jar of jam. You expect a few flavors, maybe 6 or 7. But instead, you find a wall of options, dozens of kinds, each with different fruit, sugar levels, textures, and brands. You try to scan them all, but the more you look, the harder it gets to pick. You start to worry that you'll choose the wrong one. You feel pressure to make the best choice. After 10 minutes, you grab one just to end the stress. When you get home, you taste it, and all you can think about is whether one of the other jars would have been better. This is the paradox of choice. Psychologists have studied this effect in real settings. One famous experiment offered people a chance to taste jam at a market booth. Some people saw only 6 types. Others saw 24. The ones with more choices were more likely to stop and sample, but they were far less likely to actually buy a jar. The people who saw fewer options made decisions more easily and felt more satisfied afterward. The larger set of choices led to more interest, but it also led to more doubt, hesitation, and second-guessing. This is called decision paralysis. When faced with too many options, people often freeze. They delay the choice or avoid it completely. They think they should wait until they have more time to compare, or they walk away, unsure of what to do. This happens with simple choices, like choosing a snack, but also with bigger ones, like picking a college, a career path, or a place to live. The more options you face, the harder it is to feel confident. Even when people do choose, more options often lead to regret. When you have only a few options, you accept the one you choose more easily. But when you have dozens or hundreds, the odds that you pick the best one feel smaller. You start to wonder, what if I'd chosen something else? That thought lingers. It turns a good choice into a source of doubt. You imagine the other options as better than they really were. That's regret, and it grows as the number of options increases. There's also the problem of raised expectations. When you have more choices, you expect more from the outcome. If you can pick from 50 shirts, the one you choose had better fit perfectly. If it doesn't, you're disappointed, even if it's a good shirt. If you had only 3 options, you might feel satisfied with a less than perfect result. Your expectations would have been lower, but with more options, you feel that perfection should be possible. That makes disappointment more likely, not less. This applies to many parts of life. In relationships, dating apps offer hundreds of profiles. People swipe endlessly, looking for the best match. But with so many choices, commitment becomes harder. Every match feels replaceable. People compare constantly, wondering if they could do better. That mindset makes it difficult to feel content. It shifts the focus from building a connection to evaluating options. In the workplace, employees are told they can design their own path. They can move departments, switch roles, or redefine their job. But some feel overwhelmed. They don't know which direction to take. They fear choosing wrong. They spend more time thinking about where to go than actually going anywhere. The freedom, while meant to empower, becomes a source of anxiety. In education, students are offered long lists of classes, majors, and tracks. That variety seems great at first, but students often feel stuck trying to choose the right path. They delay decisions, switch majors, or doubt their choices. Fewer, clearer options might help them move forward with more confidence. Not all choice is bad. Some choice is necessary. Without it, people feel trapped. They need options to feel free. But there is a tipping point. Once the number of choices becomes too large, the benefits start to disappear. The brain has limits. It can only compare so many things at once. When faced with too much information, people start to simplify. They rely on shortcuts. They go with what feels safe, or they don't choose at all. One way people cope is by choosing good enough instead of best. This is called satisficing. A satisficer picks something that meets their needs, even if it's not perfect. A maximizer, in contrast, keeps searching for the best possible option. Maximizers are more likely to feel regret, even if their choices are objectively better. They struggle with what-ifs. They focus on what they missed, not what they gained. Satisficers tend to be happier because they accept trade-offs and move on. To deal with the paradox of choice, some people set personal rules. They limit the options they consider. They decide in advance what matters most. They stop looking once they find something that meets their needs. These rules reduce stress and protect against regret. They don't guarantee perfect outcomes, but they make decision-making more manageable. Stores and websites have started to adjust as well. Some now offer fewer options or recommend bestsellers. They highlight a few picks instead of showing everything at once. This helps customers make faster, easier choices. They feel less overwhelmed. They're more likely to buy and more likely to feel good about what they picked. The paradox of choice reminds us that freedom and happiness don't always grow together. More choice offers more control, but only up to a point. After that, it adds noise, stress, and second-guessing. When every option competes for attention, it becomes harder to feel sure. When too many paths lie ahead, people often stand still. The solution is not to remove choice, but to understand its limits. Clear boundaries, simple goals, and a focus on what matters most can help people choose with more ease and live with more peace. The paradox of value asks a simple but confusing question. Why is water, which is essential to life, so cheap, while diamonds, which we don't need to survive, are so expensive? You need water every day. You can't live without it, yet you pay very little for it. On the other hand, diamonds serve almost no practical purpose. They don't keep you alive, but people pay thousands of dollars for them. This goes against what many people expect about value. You might think that things which are more useful should cost more, but that's not how prices work. This is the heart of the paradox. The problem was described clearly by Adam Smith, the 18th century economist and philosopher. He pointed out that water has great use value, but little exchange value. You use it all the time, but you can't trade it for much. Diamonds are the opposite. They have high exchange value, but little real use. This seems wrong at first. It makes it look like markets ignore what really matters. To understand the solution, you have to shift how you think about value. It's not based on how much something is used overall, but on how useful the next unit of it is. Economists call this idea marginal utility. The word marginal here means the next one, the next glass of water, the next diamond, the next bite of food. The value of something depends on how much benefit you get from one more of it, not from all of it. Now think about water again. It's everywhere. You can turn on a tap, fill a glass, take a shower, wash your clothes. Because water is abundant, the next glass doesn't add much to your life. You already have what you need. So the marginal utility of that next glass is low. You might enjoy it, but you don't need it badly. That's why the price is low. Diamonds are rare. You almost never come across one in daily life. If you do get one, it's special. There are fewer of them to go around. That makes the next diamond much more desirable to someone who values it. It might be used in a gift or a piece of jewelry. Even if the use is symbolic, the demand is strong and the supply is limited. So the marginal utility of the next diamond is high. That leads to a higher price. This way of thinking helps explain many pricing patterns in the world. Consider air. It's even more essential than water. You die without it in minutes. But air is free. Why? Because it's unlimited. The next breath costs nothing, because it's always there. Now think about something less essential but less available, like a movie ticket. You don't need movies to live, but people pay for tickets. That's because access is limited. The experience is unique. The value of the next movie you watch is higher than the next breath of air, in terms of scarcity and enjoyment. The same logic applies to food. Imagine a person at a buffet. The first plate of food has high value. You're hungry, and you enjoy every bite. The second plate is still good, but not as great. By the third, you're full. The fourth is too much. The value of each extra plate drops. That's diminishing marginal utility. The more you have of something, the less each additional unit matters to you. That's why people are willing to pay more for the first plate than for the fifth. Now apply this to water. In a desert where water is scarce, the price rises. If you're thirsty and there's only one bottle left, its marginal utility is very high. You'll pay more for it. The same bottle costs less in a city with clean tap water. The product didn't change, just the context. Scarcity plays a major role in this. Diamonds are not just rare in nature, they're also controlled in supply. Companies that mine diamonds release them in limited amounts to maintain high prices. Scarcity increases perceived value. Even though the actual use of a diamond is limited, the fact that not everyone can have one adds to its price. People buy diamonds not just for what they do, but for what they represent. That's still part of utility. It's just social, not practical. Prices are set by markets. They reflect how much people are willing to pay for the next unit of something. They don't always match the total usefulness of an item. Instead, they match what that item does for someone right now, based on how much of it they already have. That's why essential things like water can cost little, and non-essential things like diamonds can cost a lot. Imagine a world where diamonds were everywhere. You could pick them off the ground like stones. Their price would crash. No one would pay thousands for a ring. They would become decoration, not status symbols. The same goes for water. If clean water were rare, it would become precious. People would fight over it. That happens in places where water is limited. Prices go up. Value shifts with access. This paradox also shows how markets often focus on individual preferences, not social needs. What matters to survival doesn't always matter in pricing. A medicine that saves lives might still be cheap if supply is high and production is easy. A luxury watch might cost more than a life-saving drug if people are willing to pay more for it. That's not because the watch is more useful, but because the people buying it value it more in that moment, and the supply is tighter. In daily life, we all apply marginal thinking without knowing it. We judge whether we need one more pair of shoes, one more snack, one more streaming subscription. We make choices based on what we already have. If we lack something, we value the next unit more. If we have plenty, the next one seems less important. That logic shows up in every market, from groceries to real estate to luxury goods. The paradox of value isn't really a contradiction. It just shows that value comes from context, not just from usefulness. The total need for something matters less than the situation you're in and how much more of that thing you want. Once you understand marginal utility, the puzzle solves itself. You stop asking why water is cheap and diamonds are expensive. You start asking, how badly do people want the next one? How many do they already have? What's the supply like? That's how markets think, and that's how prices get made. The GRU paradox starts with a strange word and a simple idea. The word is GRU. It describes something that is green before a certain time, call it time t, and blue after that time. So an emerald that is green today but turns blue tomorrow would be called GRU. If it stays green forever, it's not GRU. The concept feels made up, but it raises a deep question about how we form beliefs based on the past. Imagine you've been looking at emeralds for years. Every emerald you've ever seen has been green. You've used that experience to form a belief. All emeralds are green. That's how induction works. You observe a pattern and use it to make a general rule. It's not guaranteed to be true, but it feels reasonable. Now think about the word GRU. Every emerald you've seen so far is also GRU. Why? Because it was green before time t. You didn't know the word before, but the description fits. So your past observations support the idea that all emeralds are green, and also that all emeralds are GRU. But these two predictions don't match. One says future emeralds will be green. The other says future emeralds will be blue. Which one should you trust? That's the paradox. Why do we trust green as the natural way to describe emeralds, but not GRU? Both match past experience. Both explain what we've seen. But only one seems right when predicting the future. We say future emeralds will be green. We don't say they'll be GRU, even though the evidence supports both ideas. The question is, what makes one prediction more reasonable than the other? The problem is a challenge to induction, the method of drawing general rules from past observations. Induction assumes that the future will resemble the past, but the GRU paradox shows that this depends on how we describe what we've seen. If we change the words, we change the rules. If GRU counts as a valid color, then maybe future emeralds won't be green. Maybe they'll turn blue. The paradox forces us to ask why we think green is a better choice than GRU. One answer is that green feels simpler. It's a basic property. GRU is complicated. It mixes color and time. We're used to describing things by what they are now, not by what they'll become. So we prefer terms like green that don't rely on future conditions. This view says that some properties are more natural than others. Green is a natural color. GRU is a strange invention. But the paradox pushes harder. It asks, what counts as a natural property? That seems like a subjective decision. For someone raised with GRU as a basic word, green might seem like the strange one. That person would expect emeralds to be GRU. The difference isn't in the evidence, it's in the language. So the paradox becomes a question about how we choose which descriptions to use. This leads to deeper issues in philosophy. Induction relies on regularity. We believe that the world follows patterns, and those patterns will continue. But the GRU paradox shows that patterns depend on how we describe the world. If we describe things one way, we get one pattern. If we describe them another way, we get a different pattern. That shakes the foundation of inductive reasoning. It suggests that there's no neutral way to project the future. Every prediction comes from a choice about how to describe the past. The philosopher Nelson Goodman introduced the paradox to explore this issue. He wanted to show that induction isn't just about evidence, it's about the language we use to make sense of it. We don't just see green emeralds. We also choose to call them green, not GRU. That choice shapes what we expect in the future. So induction depends on a hidden structure of concepts. It's not purely logical, it's partly linguistic. Some philosophers respond by saying that we should only use projectable predicates, terms that lead to stable predictions. Green is projectable. GRU is not. But that brings us back to the original problem. What makes a predicate projectable? We can't say it's because it leads to the right prediction, since that's what we're trying to figure out. We also can't say it's because of past experience, since green and GRU match the same experience. So the choice remains unexplained. Others argue that we rely on background knowledge. We know something about how color works. We think that emeralds stay green because of their structure. That makes green a better fit. We don't have a reason to think they'll suddenly turn blue after time t. That makes GRU look suspicious. But this response assumes we already have a theory of emeralds. It moves the problem from induction to explanation. Instead of just observing emeralds, we try to understand them. The prediction comes from a theory, not just from a pattern. That's a valid move. It shows that real reasoning is more than just collecting data. It involves models, causes, and context. We don't treat all descriptions as equal. We pick the ones that fit with what we know. That helps us avoid strange concepts like GRU. But it also means that induction isn't self-contained. It depends on other parts of knowledge. In the end, the GRU paradox doesn't destroy induction, but it shows that induction is not as simple as it seems. You can't just look at past cases and project forward. You have to decide which features matter. You have to choose how to describe what you've seen, and that choice affects what you believe about the future. The paradox asks us to think more carefully about how we learn from experience. It reminds us that even basic ideas, like color, are shaped by how we talk about the world. It shows that evidence alone doesn't guide belief. It's filtered through the concepts we use, and those concepts carry assumptions, patterns, and expectations. When those assumptions shift, so do the patterns we see. So the question raised by GRU is not just about emeralds. It's about what we count as normal and why. It's about how we decide that one way of describing the world makes more sense than another. And it's about what that means for the way we reason, predict, and understand what comes next. Quine's paradox is a puzzle about language, logic, and self-reference. It centers on a sentence that refers to itself in a strange and indirect way. The sentence is this: yields falsehood when preceded by its quotation. Yields falsehood when preceded by its quotation. At first glance, it's confusing. It looks like a string of words that folds in on itself. But when you slow down and unpack it, it reveals a deep problem, one that touches the limits of what formal languages can express without running into contradiction. To understand what this sentence is doing, it helps to take it apart. Start with the inner part. Yields falsehood when preceded by its quotation. This is a phrase, not yet a sentence. It describes what might happen when that phrase is quoted and placed before itself. The sentence says, when you take this phrase, put its quotation in front of it, and then read the whole thing, the result is false. So we try it. We take the phrase, yields falsehood when preceded by its quotation, and put its quotation mark version in front. That gives us the full sentence, yields falsehood when preceded by its quotation, yields falsehood when preceded by its quotation. This is now a complete sentence that talks about itself. It's making a claim about its own truth value. It says, if you build this sentence using the quoted phrase, the sentence will be false. Now the question is the sentence true or false? If it is true, then what it says must be the case. It says that the sentence yields falsehood. So if it's true, then it must be false. But if it's false, then what it says isn't the case. It doesn't yield falsehood. That would mean it's actually true. So either way, you hit a contradiction. If it's true, then it's false. If it's false, then it's true. That's the paradox. This kind of self-referential twist is similar to the classic liar paradox, which says, this sentence is false. That sentence creates the same loop. If it's true, it must be false. If it's false, it must be true. But Quine's version is more subtle. It avoids saying this sentence directly. Instead, it uses quotation and description to create self-reference without pointing at itself so clearly. That's what makes Quine's paradox interesting. It shows that you can build self-reference into a sentence just by arranging language the right way. You don't need a word like this. You don't even need a direct pointer. All you need is a sentence that describes a condition that includes its own form. The paradox arises naturally from how symbols can refer to other symbols, even when those symbols are part of the same system. This raises questions about truth in formal systems. In formal logic, especially in mathematical logic, we often want a system to say true things about itself. But paradoxes like this one show that's not always possible. When a system becomes powerful enough to talk about its own sentences, it opens the door to contradiction. You can build sentences that refer to themselves in ways that trap the system in a loop. This was one of the major discoveries of 20th century logic. Mathematicians like Kurt Gödel showed that no formal system can be both complete and consistent if it's strong enough to express arithmetic. That means there will always be true statements that can't be proven within the system, and some statements that create contradictions if you try to assign them a clear truth value. Quine's paradox is a simple example of how that happens. In this case, the problem isn't about math, it's about language. But the same rules apply. Formal languages work by using symbols according to strict rules. They let us define terms, state facts, and draw conclusions. But they also let us create sentences that refer to other sentences, or even to themselves. And when that happens, things can break down. One way to deal with the problem is to restrict the language. You can set up rules that block self-reference. For example, you can separate the language used to talk about things, the object language, from the language used to talk about statements, the meta-language. That way, no sentence can refer to itself directly because it's always one step removed. This is how some logical systems try to avoid paradoxes. But that solution has limits. In real life, we use self-reference all the time. We talk about sentences, beliefs, and thoughts that refer to themselves or to each other. Our natural language allows this freely. So any system that avoids self-reference completely doesn't match how we actually speak and reason. It becomes safe, but less useful. Another way to approach the paradox is to accept that some sentences don't have a truth value. They're not true, and they're not false. They're just undefined. Some logical systems adopt this view. They treat paradoxical statements as outside the range of truth. They still exist in the language, but they can't be assigned a value without creating contradiction. That's a practical fix. But it also shows that our idea of truth has limits. We usually think that every sentence is either true or false. That's the law of the excluded middle. But paradoxes like Quine's suggest that this law doesn't always hold. Some sentences break the rule, not by being vague, but by turning truth against itself. Quine's paradox is also a reminder that language is a tool. It's powerful, flexible, and useful, but not perfect. When we build sentences that refer to themselves in just the right way, we can create traps. These traps don't reflect problems in the world. They reflect the shape of the tool we're using. They show the edge where language starts to eat its own tail. That doesn't make language less valuable. It just means we have to use it carefully. In formal logic, it means setting boundaries around what kinds of sentences are allowed. In everyday life, it means being aware of when words start to loop back on themselves. Most of the time, we don't need to worry about this. But when we push language to its limits, as in logic, philosophy, or computation, these issues matter. Quine's paradox is short, elegant, and troubling. It takes a simple sentence and turns it into a mirror. It forces us to think about what happens when words reflect themselves, and how that reflection can break our normal ideas of truth. It shows that even in a world built on logic, there are corners where logic starts to fold in on itself. And in those corners, we learn something important, not just about language, but about the limits of what any system can say about itself. The preface paradox begins with a familiar situation. An author writes a book. They work carefully, check facts, edit drafts, and revise each chapter. After months of effort, they publish the book. In the preface, they thank readers and add one honest note. While I believe everything I have written is true, I also recognize the possibility that the book may contain some errors. This sentence seems reasonable. Authors are not perfect. Mistakes happen. But this small admission leads to a puzzle in logic and belief. The author claims to believe every statement in the book. That means they believe Chapter 1 is accurate, Chapter 2 is accurate, and so on. They believe each claim in the book is true. At the same time, they also believe that at least one claim in the book might be false. This seems inconsistent. How can a person believe that every part is true while also believing that the whole may contain errors? That's the paradox. It's easy to relate to this situation. You might write a research paper or submit a report. You believe each part is correct. But if someone asks you whether there could be a mistake somewhere, you admit that it's possible. You don't know where the mistake is, but the chance exists. This belief is based on past experience. You've made mistakes before, even when you were confident. You've seen others make similar errors. So your belief that errors are possible seems rational. This leads to the central question of the paradox. Can a person rationally believe every statement in a book, while also rationally believing that at least one of them is wrong? If belief must be logically consistent, then no. Believing all statements are true and that at least one is false is a contradiction. But if belief is allowed to reflect uncertainty and risk, then maybe it's not a contradiction after all. One way to understand this is by thinking about probability. Suppose a book contains 100 factual statements. You have checked each one carefully and found no mistakes. You believe that each statement has a 99% chance of being true. That's a high level of confidence. But when you look at the whole book, the chance that all 100 statements are correct drops. Statistically, there's a strong chance that at least one of them is wrong. That doesn't mean you know which one is wrong. You still believe in each of them, but you also recognize the risk that an error slipped through. This is a form of rational uncertainty. This kind of belief is common in real life. Doctors believe in each part of a diagnosis, but also consider the chance of error. Engineers trust their designs, but run safety tests. Students believe their answers on an exam are correct, but double-check them. In each case, people believe specific claims and also accept that the overall system might include a mistake. This isn't irrational, it's realistic. Philosophers call this kind of thinking probabilistic belief. It allows for degrees of confidence. You don't need full certainty to hold a belief. You just need enough support to treat it as true for practical purposes. At the same time, you accept that errors are possible. This creates room for what might seem like contradiction, but is actually a reflection of complex thinking. The paradox shows the gap between formal logic and real human reasoning. Formal logic says that if you believe A and you believe B, and A and B can't both be true, then your beliefs are inconsistent. But human beliefs are often based on incomplete information, memory, experience, and judgment. We don't hold each belief in isolation. We collect them, use them, and adjust them as we go. That system isn't always perfectly logical, but it works. One approach to the paradox is to accept a relaxed view of rationality. This view says that it's rational to believe in things that are highly likely, even if the full set of beliefs might include a contradiction. As long as each individual belief has strong support, the overall belief system can tolerate some risk. This is especially true in large sets of beliefs. The more claims you hold, the more likely that some might conflict. But you don't need to discard all of them. You just stay open to correction. Another response is to divide belief into two types, specific and general. The author believes specific statements are true, each fact in the book, but they also believe in general that errors can happen. This general belief is about the nature of complex work, not about any one claim. It reflects a broad awareness, not a targeted doubt. That helps explain why the beliefs can coexist. One applies to parts, the other applies to the whole. Think of it like checking your luggage before a flight. You believe each item is packed. You check your toothbrush, passport, and charger. You believe each one is there, but you also worry that you might have forgotten something. That doesn't mean you know what's missing. You still believe each item is present, but you know from past trips that small things are often overlooked. That general belief doesn't cancel your specific beliefs. It just puts them in context. The preface paradox also raises questions about how belief works in groups. Imagine a team of scientists writing a paper. Each scientist believes in their part of the work. Together, they believe the paper is sound, but they also agree that research can include hidden errors. They publish with confidence, but also with caution. Their beliefs are shaped by experience, not just logic. That's how belief works in collaborative, uncertain environments. In the case of the author, the preface statement is not a confession of contradiction. It's a sign of intellectual honesty. It shows that the author trusts their work, but doesn't pretend to be perfect. This attitude strengthens the work because it shows openness to feedback and correction. It allows readers to approach the book with interest and a clear view of how truth is pursued, not as a fixed thing, but as something built carefully, with room for doubt. The paradox teaches us that belief is not just a matter of yes or no. It's a system of judgments, shaped by evidence, trust, and humility. It accepts that knowledge grows through effort and revision, and it reminds us that admitting possible error is not a weakness in belief. It's part of what makes belief strong. Got it. Here's the revised version of the Sleeping Beauty paradox, written in 1,000 words, with the betting example narrated without the $sign. The Sleeping Beauty paradox begins with a strange setup. A researcher tells Sleeping Beauty that she will take part in an experiment starting Sunday night. They will put her to sleep and then flip a fair coin. If the coin lands heads, she will be woken up once on Monday. If the coin lands tails, she will be woken up twice, once on Monday and again on Tuesday. After each waking, she will be given a drug that erases her memory of the awakening. So no matter what, when she wakes up, she won't know what day it is or whether she has been woken before. The question is simple but puzzling. When she wakes up during the experiment, what should she believe is the probability that the coin landed heads? There are two popular answers. One says the probability is 1/2. This is called the Haffer view. It says that the coin was fair, and nothing that happens during the experiment changes that. Beauty knew in advance that the coin was fair. She knew what the experiment would involve. Waking up without any new information shouldn't change her belief. She already expected that she would wake up whether it was Monday or Tuesday, and whether it was heads or tails. So waking up gives her no reason to revise her estimate. The coin still has a 50% chance of being heads. The other answer says the probability is 1/3. This is called the thirder view. It focuses on the number of possible waking moments. If the coin lands heads, there is only one waking, on Monday. If the coin lands tails, there are 2 wakings, Monday and Tuesday. Each of those wakings is just as likely from Beauty's point of view when she opens her eyes. She doesn't know whether it's the first or second waking, or which day it is. So if you count each waking equally, then out of 3 possible wakings, only 1 happens if the coin is heads. That's 1 out of 3. The reasoning says that being awake means you are more likely in one of the 2 tails situations than in the single heads one. This disagreement is not about math, it's about how to interpret probability. The Haffer view follows the classic definition of probability. It treats the coin flip as the only uncertain part of the experiment. Since Beauty knows the structure of the experiment, and nothing new has happened to surprise her, there's no reason to update her belief. She expected to wake up either way. So even after waking up, she should still assign a 50% chance to heads. The thirder view follows a frequentist idea. It looks at all the situations where Beauty might find herself. Imagine the experiment was repeated many times. Every time the coin lands heads, there's one awakening. Every time it lands tails, there are two. So in a large number of trials, 2/3 of the wakings happen during a tails outcome. That means if you find yourself waking up with no memory of which day it is, it's more likely you're in one of the tails cases. This shifts the probability. To make this clearer, suppose you repeat the experiment 300 times. The coin lands heads in about 150 of those. That gives you 150 wakings from heads. The coin lands tails in the other 150 cases, each creating 2 wakings, Monday and Tuesday. That results in 300 wakings from tails. Now you have 450 total wakings. Out of those, only 150 are from heads. So if Beauty is waking up in one of those 450 instances and doesn't know which day it is, there's only a 1 in 3 chance that she's in a heads waking. That's why the thirder position sees 1/3 as the better answer. Some people argue that the thirder view confuses memory loss with new evidence. Beauty knew from the start that memory erasure would happen. So the fact that she doesn't know what day it is shouldn't surprise her. The Haffer view says she shouldn't change her belief unless something unexpected happens. But waking up without knowing the day was part of the plan. So it's not new evidence, it's expected. Others say that from her point of view, being awake is evidence. She could have been asleep. If she finds herself awake and there are more wakings during tails outcomes, that should shift her belief toward tails. This treats being awake as a kind of data point, an observation that should influence her estimate. Another way to look at the difference is through a betting example. Imagine that each time Beauty wakes up, she's offered a bet. She can choose to bet on the coin having landed heads. If she is right, she receives 2 tokens. If she is wrong, she gets nothing. Each bet costs her 1 token. If she believes the chance of heads is 1/2, the bet looks fair. She stands to double her stake half the time. But if she believes the probability is 1/3, the bet becomes a losing one in the long run. To see how this plays out, imagine the experiment runs 300 times. In 150 of those, the coin lands heads. She wakes up once per trial and wins 2 tokens each time she bets correctly. That gives her a total of 300 tokens from 150 successful bets. In the other 150 trials, the coin lands tails. She wakes up twice each time and makes 300 losing bets, 1 in each waking. She loses 1 token per bet, resulting in a total loss of 300 tokens. At the end, her gains and losses cancel out. But she has made 450 bets in total. 150 winning, 300 losing. This means that over time, each individual bet results in a net loss. That supports the idea that the true probability of winning is 1/3, not 1/2. The Sleeping Beauty paradox doesn't just test our understanding of probability. It reveals how different interpretations of belief and evidence can lead to different answers. Some treat probability as a measure of uncertainty, tied only to physical events like a coin flip. Others see it as something tied to how often a certain situation would happen across many repetitions. What makes this paradox powerful is that both views feel internally consistent. Each uses a clear logic. The disagreement lies in what counts as evidence and how we measure likelihood when a person's experience is part of the setup. Sleeping Beauty's confusion is our own. We have to decide whether to trust the fairness of the coin or the number of times she finds herself in one scenario versus another. Either way, the paradox forces us to look closely at what it means to say something is likely. and whether that likelihood depends on what you know or where you are. Empel's paradox, also called the raven paradox, begins with a simple idea: all ravens are black. This is a general statement, a universal claim. It means that if something is a raven, then it must be black. To test this statement, you might look at ravens. If you see a black raven, that supports the statement. If you ever see a raven that isn't black, that would disprove it. This seems straightforward, but the paradox appears when you ask, what else counts as evidence? The paradox comes from a logical principle about how confirmation works. In formal logic, a statement like, all ravens are black, is logically equivalent to if something is not black, then it is not a raven. This is the contrapositive of the original statement, and in logic, a statement and its contrapositive always carry the same truth value. So if one is true, the other must be true. That part is not controversial. But now think about what confirms the contrapositive. If you see a white shoe, for example, that is something that is not black and not a raven. That fits the form, if not black, then not raven. So logically, it confirms the contrapositive. Since the contrapositive is equivalent to the original statement, that means the white shoe confirms that all ravens are black. This is where the paradox appears. How can seeing a white shoe, a thing that has nothing to do with ravens, possibly support a claim about ravens? It feels absurd. You didn't look at a bird. You didn't study its color. You just saw a shoe. That should not count as evidence for a claim about bird color. Yet formal logic says it does. To understand this, think about confirmation in a basic way. If you want to test all ravens are black, you need to check objects that could falsify it. That means you look for ravens and see what color they are. The more black ravens you observe, the more confident you become in the statement. But the white shoe? That doesn't even enter the category of things that could make the statement false. So in practice, it seems irrelevant. But logic works differently. It focuses on structure. The structure of all ravens are black is the same as if something is a raven, then it is black. Its contrapositive is, if something is not black, then it is not a raven. So anything that matches not black and not a raven fits the contrapositive. That includes many objects: white shoes, green apples, red cars, and each one, in a formal sense, confirms the statement. Still, most people feel that there's a difference between these kinds of evidence. Seeing a black raven seems like strong support. Seeing a white shoe seems like weak support or even irrelevant. Philosophers and scientists try to explain this by introducing ideas from confirmation theory. The main idea is that not all evidence confirms a statement to the same degree. Some observations increase our confidence more than others. Here's one way to think about it. Imagine you have 10,000 objects. Only a few of them are ravens. Most are other things: rocks, chairs, phones. If you check one of those non-black objects and find that it is not a raven, that tells you something, but it tells you very little. That's because there are already so many non-black things that are not ravens. The observation was expected. It doesn't rule anything out. It doesn't change your belief much. Now imagine you check a raven and it's black. That matters more. Ravens are rare, and if you ever saw a raven that wasn't black, the whole statement would be false. So each new black raven you observe reduces the risk of finding a counterexample. That's why it confirms the statement more strongly. So, while logic treats every confirming instance as equal, confirmation theory tries to capture the difference in impact. It uses ideas from probability. If an observation makes a big change to how likely a statement is, it gives strong confirmation. If it barely changes the likelihood, it gives weak confirmation. Another way to look at it is through filters. Suppose you're doing a study. You choose to look only at ravens. You're interested in color. So you collect data on bird feathers. You see hundreds of black ravens. That's targeted observation. Now imagine someone walks by with a white shoe. You take note of it, but it wasn't part of your study. You didn't select it because it had anything to do with ravens. You just happened to see it. That's why the white shoe feels irrelevant. It wasn't part of a test aimed at ravens. It was random. Even though it fits the logic, it doesn't fit the method. Scientific reasoning is based not just on what's logically possible, but on how we gather and interpret evidence. Context matters. This paradox also reveals a deeper tension between logic and common sense. Logic cares about structure. It says that if a statement and its contrapositive are the same, then anything that confirms one confirms the other. But human reasoning is messier. We care about cause and effect. We care about relevance and focus. That's why we judge evidence based on more than form. Some philosophers have tried to solve the paradox by changing how we define confirmation. They say that confirmation should be tied to background knowledge and expectations. If seeing a white shoe doesn't surprise you, then it doesn't confirm much. If you expect most non-black things to not be ravens, then confirming that again doesn't help, but seeing more black ravens might. It narrows the chance that you'll find a counterexample. Others point out that science often relies on sampling. You gather data from a group that represents the whole. If you sample only ravens and find they're all black, that gives you evidence. But if you sample non-black things and you find none of them are ravens, that also gives you evidence, but much less. That's because your sample was not focused on the kind of case that could break the rule. Hempel's paradox shows that even simple ideas, like testing a general claim, can lead to strange results when viewed through the lens of logic. It reminds us that logic and reasoning are not always the same. In logic, a white shoe can confirm a rule about ravens. In practice, it doesn't matter much. What matters is how surprising or informative the observation is, given what we already know. That's why science doesn't treat all confirming cases equally, even when logic does. The crocodile paradox is an old logical puzzle often told like a riddle. A crocodile has taken a child. It tells the parent, "I will return the child if you correctly predict what I will do next." The parent then says, "You will not return the child." This creates a loop. The crocodile must now decide what to do, but whatever it chooses leads to a contradiction. If the crocodile returns the child, then the parent's prediction was wrong. But the crocodile only returns the child if the parent's prediction is right. So returning the child violates the deal. But if the crocodile keeps the child, then the parent's prediction was correct. But in that case, the crocodile is supposed to return the child. No matter what the crocodile does, it breaks the condition it set. That's the paradox. This situation is strange, but it shows a deeper issue with logic and self-reference. A crocodile's promise depends on a prediction about its own action. When the prediction refers to the outcome of the condition itself, it forms a loop. The result is a system that can't make a consistent decision. That's what makes it a paradox. To understand the issue more clearly, break it down. The crocodile creates a rule. If the parent's statement about the outcome is true, the crocodile will return the child. If the statement is false, the crocodile will not return the child. Now consider what happens in both cases. First, suppose the crocodile returns the child. That means the parent's prediction, "You will not return the child," was false. So by the rule, the crocodile should not have returned the child. But it did, so it acted against its own condition. Now suppose the crocodile keeps the child. That means the prediction was true. So the crocodile should return the child, but it doesn't again. It violates the condition. The crocodile cannot satisfy the promise under this prediction. Any action it takes contradicts the terms. This is a self-referential loop. The prediction feeds into the outcome, and the outcome determines the truth of the prediction. It's like trying to build a staircase that turns back on itself. No matter how you climb, you're stuck. The paradox works like a trap built from logic itself. One way to think about it is to compare it to the liar paradox. That's the sentence, "This sentence is false." If the sentence is true, then it must be false. But if it's false, then it must be true. It creates a contradiction by talking about itself. The crocodile paradox does something similar. It sets up a condition where the decision is based on a statement that refers to that same decision. The problem arises from trying to use truth as a fixed measure in a self-referential system. When the truth of a statement depends on the outcome of an action, and that action depends on the truth of the statement, the logic breaks. There is no stable point. Each outcome undoes the reason behind it. Now imagine the crocodile had said something slightly different. Suppose it said, "I will return the child if you say I will return the child." Then the parent says, "You will return the child." That's easy. The crocodile hears a correct prediction and returns the child. There's no problem. Or suppose the parent says, "You will not return the child." Then the prediction is wrong. So the crocodile keeps the child. Again, no problem. The paradox only appears when the prediction says the child will not be returned. That statement becomes true if the crocodile keeps the child. But in that case, the crocodile is supposed to return the child. So the problem is not just the rule, it's the prediction that twists the logic. It makes the condition depend on itself. This shows the limits of how we use rules based on predictions. In most cases, predictions are external. You guess what the weather will be. You predict the outcome of a game. But in the paradox, the prediction becomes part of the system it's trying to describe. That creates instability. The system can't find a consistent answer. This kind of problem shows up in other areas too. In computer science, for example, self-referential systems can lead to loops that never end. In logic, self-reference can create contradictions that no rule can solve. These are not just games. They reveal real challenges in how we design systems of knowledge. The paradox also touches on trust and contracts. The crocodile makes a deal. "I'll do this if you say the right thing." But when the rule depends on what the other person says about the rule itself, it creates a loophole. The rule can't be fulfilled because its truth condition destroys its own logic. This would never work in a court or a real agreement because it's based on an unstable structure. You can also look at the paradox as a problem of definitions. The crocodile's promise creates a rule, but the rule is not well defined in every case. For most statements, the rule works, but with the prediction, "You will not return the child," it becomes undefined. The rule no longer tells the crocodile what to do. This is like dividing a number by 0. Mathematically possible to write, but undefined in value. Some people try to escape the paradox by saying that the crocodile should simply break the promise. Others say the parent's prediction shouldn't count if it creates a loop. But those are fixes that step outside the logic. They admit that the system itself is flawed. That's part of the point. The paradox isn't about crocodiles. It's about the structure of logic and the problems that appear when systems try to refer to themselves. In philosophy and logic, this paradox helps explain why some systems must avoid self-reference. It also supports the idea that rules need clear boundaries. When you build a condition that refers to itself, and the truth of that condition determines the action, the whole structure can collapse. That's what happens here. The crocodile paradox is simple on the surface, a riddle about a reptile and a child. But it reveals something deep. It shows that even clear promises, when tied to predictions about themselves, can become impossible to fulfill. It shows that logic has limits, not because it fails, but because some conditions turn back on themselves in a way that makes stable reasoning impossible. The Pinocchio paradox starts with a single sentence. Pinocchio says, "My nose will grow now." That sounds simple, but if you take a moment to think about it, you'll see why it creates a problem that logic can't solve so easily. Pinocchio's nose only grows when he tells a lie. That's the rule in his world. So, the question becomes, is he lying when he says this sentence? If the sentence is true, then his nose will grow, but his nose only grows when he lies. So if his nose grows, then the sentence must have been false. But if the sentence was false and he said his nose would grow, and it did, then he told the truth. That means he didn't lie, so his nose shouldn't have grown. This leads right back to where we started. Each possibility undoes itself. That's what makes it a paradox. It's similar to the liar paradox, which says, this sentence is false. If it's true, then it must be false. If it's false, then it must be true. That kind of self-reference breaks ordinary logic. But the Pinocchio paradox adds a twist: time. The sentence is about what will happen next. My nose will grow now. So it's not just about whether the sentence is true or false, but about whether a future event makes it true or false. That makes it more complex. Suppose Pinocchio says it and his nose begins to grow. That suggests he told a lie. But his sentence was, my nose will grow now. If that's happening, then it's true. But his nose grows only when he lies, so it shouldn't be growing. The growth makes the sentence true, but truth means no growth. That contradiction sits right in the middle of the sentence itself. Now suppose his nose doesn't grow. That means the sentence was false. He said it would grow, but it didn't, so he lied. And when Pinocchio lies, his nose grows, but it didn't grow, so again, we hit a contradiction. The lack of growth makes the sentence false, which should make his nose grow, which would make the sentence true, and we loop again. What makes this interesting is that the sentence is about a result that depends on the truth of the sentence itself. The sentence controls the event, and the event confirms or denies the sentence. This mutual dependence causes the paradox. If the nose grows, the sentence becomes true, so it shouldn't grow. If the nose doesn't grow, the sentence becomes false, so it should grow. The key issue is timing. In most versions of the liar paradox, the sentence is static. It says something about itself in the present. But in the Pinocchio paradox, the sentence refers to something about to happen. It uses the word now, which makes it about the next moment. This brings in temporal logic, a way of thinking about truth across time. And that's where the structure becomes unstable. You can imagine this problem more clearly if you think of a light switch that turns itself off when it's on, and turns itself on when it's off. If the switch turns on, it turns itself off. If it turns off, it turns itself on. There's no stable position. Pinocchio's sentence works the same way. The truth makes the nose grow, but the growth makes the sentence true, which means no lie, which means no growth, which makes the sentence false, and so on. One possible response is to say that the sentence is neither true nor false. Some logicians say that paradoxical statements like this should be treated as undefined. They don't have a truth value at all. That might help, but it doesn't fix the situation in Pinocchio's case, because his nose still has to either grow or not. The story rules say the nose reacts to lies, but if the sentence can't be called true or false, there's no way to decide whether it counts as a lie. So we can't predict what the nose should do. Another response is to change how we interpret the word now. Maybe the sentence refers to an exact moment that hasn't arrived yet. That would mean the sentence is about the future, not the present. So you wait and see. If the nose grows, then you say the sentence turned out to be true. If it doesn't, then it turned out to be false. But even then, we still face the same loop, because the nose's behavior depends on whether the sentence was true at the time it was said, not after. That's the twist that keeps the paradox locked. You might think that this is just a silly puzzle. After all, it's about a fictional puppet. But the core issue goes much deeper. The paradox shows how language and truth can break when we tie them to actions that react to the truth itself. These loops are common in logic and philosophy. They show up in legal reasoning, programming, ethics, and even politics. Anytime a statement turns back on itself and tries to predict or control its own result, things can get unstable. For example, think of a security system that deactivates if you say, "This system will deactivate now." If it listens and shuts down, then the statement was true, so maybe it shouldn't have listened. If it doesn't shut down, the statement was false, so maybe it should have shut down. The The system becomes confused by its own rules. The Pinocchio paradox is just a cleaner, simpler version of that same kind of problem. You could also compare it to a rule in a game that says, if this rule is ever applied, it will cancel itself. The moment you try to use the rule says you can't. But if you don't use it, maybe you were supposed to. This kind of self-canceling logic leads to systems that can't resolve themselves. Informal logic. One way to avoid these problems is to create layers of language. You separate statements about things from statements about statements. That's called a hierarchy. In such systems, a sentence can't talk about its own truth directly. It has to be described from one level up. That stops self-reference from causing a loop. But in natural language, and in stories like Pinocchio's, that hierarchy doesn't exist. Sentences can refer to anything, even themselves. And that's where paradoxes sneak in. The Pinocchio paradox is short, clever, and strange. It turns a fairy tale rule into a deep puzzle about logic. It asks a question that has no clean answer, not because we don't understand it, but because the question itself contains a contradiction. That contradiction comes from tying the truth of a statement to a real outcome that depends on the truth of the statement itself. That feedback loop has no stable resting point. The sentence keeps turning over on itself, and whatever answer you try to give, it flips to the other side. That's what makes it a paradox. You sit in a dark cinema. The screen shows a young boy standing by a grave, crying for his father. His hands shake. The music swells. You feel your chest tighten. You know this isn't real. The boy is an actor. The grave is a prop. The whole story was written in a script. Still, you feel sadness. You might even cry. This is the paradox of fiction. How do we feel genuine emotions toward things we know are made up? This paradox matters because it touches something we do every day. We watch movies, read novels, follow shows. We get scared by monsters, laugh at cartoon animals, grieve over characters who never lived. And yet, at the same time, we're aware it's all fiction. The actors go home after filming. The characters exist only on paper or screen. Still, our emotions respond as if these stories were real. That's the puzzle. It becomes a paradox when you line up three common ideas. First, people have emotions only toward things they believe are real. Second, we don't believe fictional characters or events are real. Third, we still feel emotions toward them. All three can't be true at once. Something has to give. One way to solve this is to question the first idea. Maybe emotions don't require belief. Maybe they only need imagination. When you watch a story unfold, you imagine it happening. You picture it, follow it, get absorbed in it. Your mind treats it as if it were real, not because you forget it's fiction, but because your emotions latch onto the imagined situation. Think of a child listening to a scary bedtime story. They know there's no monster under the bed, but they still shiver. The story builds an image that feels real for a moment. Adults do this too, just with more layers. We suspend disbelief, not by thinking the story is true, but by entering it on its own terms. While we watch or read, we focus on what the character feels, not on whether it's really happening. This is like a simulation. When you run a flight simulator, you're not actually flying, but you act as if you are. You react to conditions, make decisions, feel pressure. The mind can do this with emotions too. It simulates what it would feel like if the events were real. You don't need to believe in the event. You just need to picture it clearly enough. Psychologists call this process emotional contagion. When you see someone cry, even an actor, your brain mirrors the expression. You pick up the emotion. Your mind responds to cues like tone, music, body language. These triggers don't depend on belief. They rely on recognition. You see someone in pain, and your body reacts. You may not believe the pain is real, but the feeling still arises. Another way to understand this is through empathy. Empathy is the ability to feel with someone, to imagine their situation and respond emotionally. Fiction builds empathy by giving you access to a character's thoughts, fears, and hopes. You learn their story. You follow their journey. Even though they're not real, the emotional process is the same. You imagine what it's like to be them, and your emotions follow. For example, think of reading a novel where a character loses a friend. You know it's not your loss. You know the character doesn't exist, but you imagine what that moment would feel like. You see it from the character's view. You reflect on your own experiences of loss. The emotion is genuine, even if the cause is imagined. It's not confusion or error. It's how empathy works. Some critics say this response is not full emotion. It's pretend emotion. They argue that what we feel for fictional characters is like a rehearsal. We're practicing responses, not living them. But most people feel their reactions in a real way. Tears at the end of a movie are not pretend. Fear during a horror scene feels real, even when you know there's no danger. The body doesn't always wait for belief before it reacts. This kind of emotional response isn't limited to fiction either. People feel emotions from memories, dreams, or future worries. None of those are happening in the present, but they still move us. You can feel joy thinking. You sit in a dark cinema. The screen shows a young boy standing by a grave, crying for his father. His hands shake. The music swells. You feel your chest tighten. You know this isn't real. The boy is an actor. The grave is a prop. The whole story was written in a script. Still, you feel sadness. You might even cry. This is the paradox of fiction. How do we feel genuine emotions toward things we know are made up? This paradox matters because it touches something we do every day. We watch movies, read novels, follow shows. We get scared by monsters, laugh at cartoon animals, grieve over characters who never lived. And yet, at the same time, we're aware it's all fiction. The actors go home after filming. The characters exist only on paper or screen. Still, our emotions respond as if these stories were real. That's the puzzle. It becomes a paradox when you line up three common ideas. First, people have emotions only toward things they believe are real. Second, we don't believe fictional characters or events are real. Third, we still feel emotions toward them. All three can't be true at once. Something has to give. One way to solve this is to question the first idea. Maybe emotions don't require belief. Maybe they only need imagination. When you watch a story unfold, you imagine it happening. You picture it, follow it, get absorbed in it. Your mind treats it as if it were real, not because you forget it's fiction, but because your emotions latch onto the imagined situation. Think of a child listening to a scary bedtime story. They know there's no monster under the bed, but they still shiver. The story builds an image that feels real for a moment. Hilbert's hotel paradox is a thought experiment that helps people understand the strange nature of infinity. It was first proposed by the German mathematician David Hilbert. He imagined a hotel with an infinite number of rooms, each numbered 1, 2, 3, and so on, continuing forever. Every room in the hotel is occupied. There are no empty rooms. Yet, despite being full, the hotel can still make space for new guests. This goes against our usual understanding of how space works, and that's what makes it a paradox. To see how this plays out, imagine you arrive at the hotel and ask for a room. The clerk tells you that the hotel is full. Every single room is taken. But instead of turning you away, the clerk says, "No problem." He calls room 1 and asks the guest there to move to room 2. The guest in room 2 is moved to room 3 to room 4, and so on, forever. Each guest moves from room N to room N+1. Because there is no last room, there's always a new room for each guest to move into. After this shift, room 1 becomes free. You can now take that room. This is already strange. In a normal hotel, if all rooms are full, there's no space left. But in Hilbert's Hotel, which has infinitely many rooms, there is always room for more, if you can shift the guests correctly. Now imagine something even more extreme. A bus arrives carrying an infinite number of new guests. Once again, every room in the hotel is full, but the clerk has a plan. He tells each current guest to move from room N to room 2N. That means the guest in room 1 moves to room 2. Room 2 moves to room 4. Room 3 moves to room 6. Now all the even-numbered rooms are filled, and all the odd-numbered rooms are empty. The new guests can then move into the odd-numbered rooms. Guest 1 into room 1. Guest 2 into room 3. Guest 3 into room 5, and so on. Every guest, old and new, now has a room. This process continues no matter how many new guests arrive. If 1,000 buses each bring an infinite number of guests, the clerk can still find a way to fit them in. The hotel can stretch in ways that make no sense in our usual world but are completely valid in mathematics. The paradox doesn't mean there's a real contradiction. It's not that infinity is broken or wrong. Instead, it shows that infinity behaves differently from finite numbers. In everyday life, if you have 10 rooms and 10 guests, you're full. You can't fit even one more person without making space. But with infinity, the rules change. That's what makes Hilbert's Hotel useful. It helps people see how infinite sets can be rearranged in ways that finite ones can't. Mathematicians explain this using set theory. In set theory, infinite sets don't always behave like we expect. The set of natural numbers, 1, 2, 3, and so on, is infinite. But you can create a one-to-one match between the natural numbers and some of their subsets. For example, the set of even numbers is a proper part of the set of natural numbers. But both are the same size in terms of cardinality. You can pair 1 with 2, 2 with 4, 3 with 6, and so on, even though the evens seem like they should be smaller. They match up perfectly with the full set. That's the key idea behind moving guests in Hilbert's Hotel. Another surprising fact from set theory is that the size of infinity can vary. The set of natural numbers is called a countably infinite set. You can list its members in order, but the set of real numbers between 0 and 1 is uncountable. You can't list them all, no matter how you try. So while both are infinite, they're not the same size. Hilbert's Hotel only works for countable infinity. If you tried to apply the same idea to uncountable sets, it wouldn't work. Hilbert's Hotel also raises questions outside of math. In physics, for example, some theories about the universe involve infinite time or space. Could actual infinity exist in reality? Could the universe behave like Hilbert's Hotel? Most scientists say no. Infinity in physics usually means very large, not truly infinite. But the paradox helps clarify what a true infinity would look like if it could exist. In philosophy, the paradox raises questions about actual versus potential infinity. Potential infinity means something that could keep growing forever, like counting numbers. Actual infinity means something already complete and endless. Hilbert's Hotel works only with actual infinity, a hotel that already has infinite rooms. Some thinkers find that idea uncomfortable. They say it doesn't fit with how the real world works. Others say it's fine in the realm of pure math, where logic, not experience, sets the rules. This paradox also shows up in computer science, especially in the design of certain algorithms. If a system can process tasks in a way that mimics infinite shifting, like in Hilbert's Hotel, it might handle dynamic or growing inputs more efficiently. The paradox helps model how systems behave under unusual conditions. It reminds developers that not everything follows finite logic. It can even be used to explain errors in thinking. People often assume that infinite means too big to change. But Hilbert's Hotel shows that infinity is not rigid. It can be rearranged endlessly. That's why it's dangerous to apply finite reasoning to infinite things. Our normal sense of addition, subtraction, and space doesn't always hold. You can also imagine how strange it would feel to be a guest in the hotel. Suppose you were in room 145. One night, the clerk knocks and asks you to move to room 290. You grumble but agree. A week later, another group arrives. You're moved again, this time to room 580. Then room 1160. Every time new guests show up, your room number doubles. You never get kicked out, but you never stay in one place either. In a hotel like this, change is constant. Even if you stay forever, you'll never stop moving. Hilbert's Hotel doesn't exist in the real world, but it gives us a clear picture of what infinity means. It shows that logic can take us places that experience never does. The rules of math don't bend. They just lead to new ways of understanding. By using the simple image of a hotel and its guests, the paradox makes a complex idea easier to grasp. Infinity may never check in for a night, but it definitely makes you think.